All right, folks, let's get settled down. Yeah, okay. Very good morning. And thank you so much for coming on a Saturday morning. I am very sure that all of us understand every single one of us is kind of passionate about the open source community, be it any community. I don't want to pinpoint a single community. The fact that on a Saturday morning, after 5 long work days, you chose to wake up. I'm not sure about your breakfast status, but yeah, thank you. Regardless of that, you are here, very attentive. I'm sure you're expecting a very good lineup of talks, and it's a commitment from our end that you will have very productive first half of the day. Couple of housekeeping items before we start. We have tea and coffee at the back end on the at the counter, so please help yourself. If someone is looking for restroom, washroom, it's on the ground floor. There's a main gate. Exit and take a left and then take another left. If you need to wash your hands or face or just get freshen up, we have the sink area in the back end. We have lunch. So yeah, so please ensure that you are grabbing the lunch, and the speakers as well as the organizers will be hanging around during the networking section. We are planning to have the networking section for about 60 to 90 minutes post our last talk. We will be having a very short 5 minute speech from the Cloudera TA, talent acquisition team, just in case if anybody is interested. So yeah, you can grab the TA person as well and just try to have your questions answered. I'm not sure about our collaborators, but we have TAs from them as well. If I can invite Fredson and Harsha with me. Yeah. All right. In the meantime, how many of us are visiting a Cloudera or attending a Cloudera meetup for the first time? For the first time. Absolutely first time. You have never stepped your foot inside Cloudera premises. All right. Oh, we have a couple of speakers as well. Yeah, you can come here. You can come here. All right. All right. Who is attending for the second time? Second time. All right. I see very proud hands in the air. Who is attending for the third time? Yes. Third time. Okay. Just two hands. Can you raise it a bit like this? Okay. Fourth time. Anybody here is? Where were you for the third time? All right. All right. Are you sure? Perfect. Perfect. So we have just one attendee attending a Cloudera event for fourth time. Anybody else? Fifth Cloudera event? Fifth Cloudera event? All right. Big round of applause. All right. You, sir, have made yourself entitled for a very exclusive swag. So during the networking section, please reach out to one of us and we'll be helping you with a nice swag. All right. Now, I think this is enough to get you motivated to step inside the premises every Saturday, not every Saturday, once every 4 weeks. We'll be having our next meetup probably around the last Saturday of the next month. So please keep an eye on the invitations and the LinkedIn and Meetup correspondence as well. All right. So we have Harsha with me as well as Fredson with me. Cloudera is collaborating with DataZip and E6 Data as well. So it's a collaborative meetup. This is, I think, a very rare occasion that three companies from Bangalore are coming together. And that's the reason that we have chosen to name this meetup as Bangalore Meetup. So yeah, Bangalore Data Lakehouse Meetup. So I think it's a very fitting description. With that, all right. So again, a warm welcome. We have our first speaker of the day, and he's also going to present the keynote talk. Please welcome Andrew Madsen. So just one word of advice. So I'll be giving a description and the introduction for all the speakers. This is out of respect for them, of course, but this is also to let you know that what tech stack they are working upon, what has been their history and what currently they're doing. So this is going to help you understand what kind of topics and what kind of interactions you can have with them during the networking section, right? So if you think it from that point of view, the description becomes very important. And yeah, so just try to pay attention to their description, and it's going to help you understand who they are. So let me start with this. Andrew is the head of developer relations at Fivetran, where he works with data teams building next generation data infrastructure across Apache Iceberg, data lakehouses, and AI infrastructure. He is an O'Reilly author, co-authoring Apache Polaris, the definitive guide, and currently writing data transformation. The definitive guide and AI ready data with 250K plus community members around or across YouTube, LinkedIn, and on his newsletter. He has delivered 50 plus keynote presentations across the world. I think I just spoke with him. He is traveling from Munich straight away to this meetup. So again, I think he deserves another round of applause just for this. Andrew brings both practitioner depth and community reach to everything he does in the open data space. So I think he's definitely the go-to guy during the networking section. All right, I'll be handing over the mic to him. And yeah.
Awesome. Thank you so much. Big hand for our sponsors, Cloudera, E6 Data, and Olake. How many screens are there? There's two? Okay. Great. Well, I'm thrilled to be with you today. I was giving my counterpart over at Cloudera a hard time because he's not here, and we speak a lot together. There's so much going on with Iceberg, but I want to set your expectations correct, because you know how when you go to like a comedy show or a concert, you've got an opener who's like not that good, and they set it up for the people who are awesome after them? I'm your opener. So I'm here to set your expectations low so that they blow your mind away. I was looking at what they're planning on presenting, a lot of incredible topics that we're going to cover today. So just a little bit about myself. Why should you listen to me? You probably shouldn't, but I'll tell you a little bit about myself anyway. So head of developer relations at Fivetran, at least I was. We just completed our merger with DBT Labs, so I'm hoping my new job title is employed. We will see. I joined Fivetran from an acquisition. They bought Tabico Data. At Tabico, we created SQL Mesh and SQL Glot, those open source projects, if you're familiar with those. Prior to that, I was the chief data officer at Dremio. Shout out to Dremio, just getting acquired by SAP, or in the process of that. Now, before that, I had real jobs where I actually led data and AI at a bunch of different places. On the side, I'm a graduate professor of data science and data engineering at a bunch of different places. But none of that matters, because I just got my silver play button on YouTube. Thank you. Thank you. So now I'm going to retire, and I'm going to be an influencer, and I'm going to be making TikToks in the parking lot after this. Okay, why are we here? Oh, we got a little more BS. I have a free copy of Apache Polaris, the definitive guide. We'll find out a way to get that to someone today. In October, I've got AI-ready data coming out. I'll find free links for that for you, so that never buy a book. There's like almost always a free link. And I recommend you get a free copy of Data Transformation, the definitive guide. This is the early release. And in October, our full book is coming out. I co-wrote this with Toby and Iroslav, creators of SQL Mesh and SQL Glot. And now that Tristan Handy is on our team, he's contributing as well. So please get a free copy of that. And when the full edited, polished version comes out in October, if you've got the early release, you'll automatically get the full book as well. I'll pop up this QR code at the end. Okay, I want to keep everything on time because I saw those other presentations and they are amazing. So what's going on? So I want to talk a little bit about AI. And, you know, AI is everywhere and it's in our face. And I'm not that old, but I'm old enough to remember when AI really just meant deep learning, right? We were just doing deep learning and neural networks, and that was AI. And then BERT comes out, we've got transformers. Now when we say AI, it's generative AI, and it's now 2026 agents. So why the popularity? Why is AI in our face all the time? Like, we've had deep learning, neural networks, we've had classical machine learning forever. Backpropagation came out in the 80s. Well, a lot of organizations that are implementing it are saying that they're seeing high ROI. So that means money. So then boards are looking at this. They're like, we like money. We would like more money. Go do AI. And so then all of us are like, oh, now we got to figure out how to do AI so that they can get more money. So it's a top-down initiative that's being pushed. And so AI is everywhere, but it's not so easy. So Gartner is showing that their estimate, and it's Gartner, so take this with it. Is this recorded? I don't want to lose any friends later in the Gartner community. Take this with a grain of salt. They're estimating 40%. And anytime I see a statistic that ends in like a 0 or a 5, it's probably made up. But 40% of agent projects, so like the whole project, not just the proof of concept, are going to be completely abandoned by the end of 2026. So everybody doing agent proof of concepts and trying to stand up a program now, Gartner's estimating that 40% of them are going to scrap it. Well, why? And what does this have to do with Iceberg? Well, there's a few reasons. I think that in order to know where we're going, and I believe the future is Iceberg and open lake houses, we have to know where we've been. And that will really help because the future is so volatile. In game theory, you have really kind of two ways of looking at the future. If there's a low probability of change, it's very stable, then you can really lock in and give up flexibility so that you can optimize for what you already know, and you're betting that past performance will mimic future performance, right? And for analytics and machine learning, that's really been the case where the requirements of our data didn't really change that much over the last 30 years. We kind of always had the same requirements for our data. So we could lock down and try to optimize for those requirements. But with AI, we're getting new models every day. We're getting new capabilities. We're getting all these new tools, like OpenClaw is a thing for a minute. Now it's NanoBot. Now it's these NemoBot and all these different things. So the future is extremely volatile. And in a volatile future where there's a lot of unpredictability, you want to optimize for flexibility. The strategy that's the most flexible, that doesn't sacrifice the integrity of the outcome, is the one that's going to win. And I would argue that with AI, having a flexible strategy for your data is what's going to win. So if we look at where we've been, we look at that 40% number of like, why is it so hard to just do AI? Like, hey, go do AI. And I was literally leading analytics at a fairly large organization when ChatGPT came out. And the president of that organization literally said those words to me. He said, go do AI. And I was like, what does that mean? Like, buy a ChatGPT license? What are we doing here? So if we think about the history of data storage, like, why is this so hard? What have we been doing that's making it difficult to implement AI now? And where does Iceberg fit in? So if you think about the beginning of data storage, and don't talk to me about like Sumerian tablets, like, no, we can go fight in the parking lot about that. We're talking in the 50s when it started going on tape. Data storage was 100% coupled together with the application, with the compute, with the metadata, with the data, and the storage. So just one all locked together component. There's a lot of benefits to that, right? We talked about when your needs are fairly well known, you can really give up flexibility and optimize for efficiency and security, those type of things. So super secure, it's transactional, it's ACID guarantees, awesome. But you can't scale independently. You can't just go add new storage to it. You can't add more compute. And if you have a new application, you've got to build the whole thing from the ground up. So all these applications are fully coupled together and they don't talk to each other. And this is really how it goes until like the 1960s, when one thing was good and it set up a good pattern for going forward, is that the application was at least split out from the data storage. But inside the data storage, the compute and the metadata and the data and the storage completely coupled together. And also they don't talk to each other. But one good thing is that now at least multiple applications could talk to the same storage, but the storage doesn't talk to each other. So we are getting a little more flexible in terms of having multiple apps talk to the same storage. And this continues until the 70s. So in the 70s, 1972, E.F. Codd writes a paper on relational databases. And this is where, boom, primary keys, foreign keys. Now we've got this concept more of data modeling. We can be a little more efficient with it. This is great. But we still have this same structure of completely coupled together data storage and applications that are talking to that data storage. But the data storage still does not talk to each other. It's still just transactional, but at least inside that data storage, we've got the concept of keys, which is great. We can be more efficient inside that storage. But again, it's just transactional. The whole purpose of this storage is to power applications. This is what keeps the lights on. This is what makes us money. We can't mess with it. 100% guarantees on ACID compliance. So great transactional systems, very rigid. Right, so we're optimizing for efficiency, guarantees, rigidity, and we're giving up flexibility for that. And then in the 1980s, Bill Inman and IBM, we've got a speaker from IBM, don't we? Where's IBM at? Nowhere? Okay, maybe I made that up. IBM, see? IBM, who just acquired Confluent. Congratulations, Confluent rules. So in the 1980s, Bill Inman and IBM have this idea, this crazy idea. They're like, hey, we've got all these siloed transactional systems which are powering the application. Great. But what if there's more value to the data? Oh, that was good. Me and my 3-year-old argue over who's the best artist, and usually I lose. So here we go. What if there's value to the data beyond just powering the application? What if we could find a way to get this data from these multiple sources into one place, one single source of truth? We've heard that before, right? And let's call this a warehouse. To get it in there, we had to create this new concept of ETL, extract, transfer, load. And then Bill Inman's idea is, hey, let's get it all centralized. Let's have one single source of truth from all of our transactional systems. We'll create an analytical database, and it's not really a database, but we're going to call it a data warehouse on-prem at this time. And that enables us to do this new thing called analytics. So this is the first time where we're really getting value from the data beyond just powering our applications. And Inman was really strict on like, hey, before we do this analytics, we have to be very strict on doing third normal form, identifying our entities, and doing this type of strict data modeling before we do analytics. But it turns out that's really hard. And so what happened was people in different business units like sales was like, hey, we want our own data to do our analytics. And then marketing's like, hey, we're special too, and we want our own data. And then HR's like, well, we have special data and we don't want anybody to see it. So we want our own data. So then we start, instead of having this idea of a single source of truth to have unified enterprise level analytics, we start getting these more silos. And then we have to do ETL jobs to get into these different warehouses. And now there is no single source of truth. So now we've just continued to expand our data landscape of transactional systems. We've added on analytical systems. Awesome. We're trying to do business intelligence and drive value that way. But we've lost the plot on single source of truth, which is what in the 90s, Ralph Kimball was witnessing. He's like, hey, this whole top-down, third normal form, like be super strict before we do anything with the data on our warehouses, it's just not working. So let's quit pretending like single source of truth is a thing, and let's just make these things called data marts, where HR and marketing and all of these business units have their own mart, and let's do this thing called dimensional modeling, bottoms-up modeling, where we're just going to optimize our data model for querying, for the analyst. So we're not thinking like enterprise-wide. We're just going to say, hey, here's the marketing data mart, and we don't care what's in the HR data mart or the sales data mart, and we don't care if they align. We just want marketing to get whatever data they want so that marketing can get their analytics. So dimensional modeling was great. And often to feed these data marts, we're doing ETL from these warehouses. They didn't really replace them. So now we have our transactional systems powering our business critical applications. We're doing ETL jobs into our warehouses. Those are all siloed and disparate. And then we're doing ETL into these data marts. And we're confused why we're having trouble with AI. We're like, we can't even do BI. And we want us to do AI? And it only gets worse because up to this point, we're just dealing with structured data. It's all rows and columns. Well, what happens in the 2000s? Harsha, keep me honest on time because I don't want to take up other people's time. You just give me the 5, shut up, get off the stage. So 2000s, internet. So now we've got the unstructured data. So now we've got images. That's an image. And we've got logs. We've got all this unstructured text. Like, oh no, that doesn't fit neatly into our janky data landscape, which is working with rows and columns, but now we've got unstructured data, so we need to drop it somewhere, and this concept of data lake comes up. And there's really kind of 2 flavors of this initially. So we've got Hadoop, HDFS, which is like a distributed file system, and then we've got S3, Amazon Web Services S3, which is like, hey, put it in here. You can just rent space on Jeff Bezos' computer, and then we'll give you an API endpoint. If you can access the endpoint, you can access your data. Fantastic. So S3 is really a big deal because that's the first time where we've separated our application, but this is the first time where we actually separate out the storage. So storage is completely separate. It can scale independently, but our compute still locks up our metadata and our data. Whatever engine you're using is writing in a proprietary format. So if you use a certain engine, you have to read also with that engine. There's no interoperability there. But at least our storage is separate and it can scale independently. It gets rid of the high overhead of having to go build something in order to scale. So this is when quote unquote data becomes the new oil. It becomes cheap. And I like the analogy of data being the new oil because yeah, it's hard to get to and it's difficult to refine and make something worthwhile out of. But anyway, this is where we get in the data lake. But the data lake went the opposite spectrum on flexibility. So if you think back to the transactional systems, even the warehouses, they're doing ACID guarantees. It's transactional. There can be no issues. And then the data lake's like, we're okay with issues. Like we want to be super flexible. This is like the hippie of data storage. We're like governance, that's okay. Delete that column. Did it really get deleted? Maybe, maybe not. So it's difficult to work with on the data lake, and we just continue adding more and more and more data. It becomes that data swamp that you hear about. And it's not like you can go tell an analyst, like, hey, go do analytics on the data lake. Like those 30 JSON files are actually a table, just like figure it out. So then you need data engineers to do ETL jobs out of the data lake and into this warehouse nightmare. So then we've got one great circle of enterprise data structure. And if you've worked in data longer than 5 minutes, this probably resonates with you. Your data landscape may look a lot like this. So this is what everybody is dealing with in the 2010s. Oh, 15 minutes? I thought I had like 2 minutes. You gave me too much time. It's okay. If you're bored, just fall asleep and I'll get off the stage super quick. So, or we'll mock you while you're asleep. Either one. So in the 2010s, 0 laughs on that. Super happy about that. You know who doesn't laugh at any jokes ever is the English. So I said that. I was in London last week giving a presentation and 0 people were laughing. And I was like, you know, you're the only group who doesn't laugh. Like, let's have fun. And they're like, well, if you were funny, then we would laugh. And I was like, oh, good. So I'm happy to be here with you today. Anyway, so this is what everybody's dealing with, like, oh, we've got all these rigid structures. We like the guarantees that we get from our warehouses, but there's no single source of truth. We like the flexibility we get from our data lake, but we can't really trust it, or we have to go through this long cleansing transformation process and dump it back in our warehouse. Marketing and sales are defining things differently. It's kind of a mess. So in 2010, well, not 2010, it's the 2010s. So 2015 through 2017, this is where Uber and Netflix and Databricks come up with the idea of, hey, we really love the flexibility and scalability, elasticity of the data lake. We hate that it's difficult to govern, that we can't really trust it. And we love the guarantees of our warehouses, but we hate the rigidity and the lock-in that comes with it. What if, crazy idea, we could have all of our files in the data lake, and we could organize that metadata in a way that tells our query engine that, hey, all those files are really a table. And this is the concept of open table formats. So Uber rolls out Apache Hudi. And if you think about that use case, like what does Uber care about? It cares about almost transactional data, aggressive vacuuming, and it wants to know real time, aggressive CDC, right? And then Databricks rolls out Delta Lake, which is really for large-scale analytics. What does Databricks rule at? 1, Spark. 2, machine learning, especially at this time. And so they really wanted a large body of data in the data lake, cheap, flexible, elastic, but also that they could trust. They want to do their feature engineering. So they come out with Delta Lake. And then the folks at Netflix are also dealing with this exact same problem, very similar to Delta Lake, where they wanted this large body of data. They wanted it to be stored in a very flexible storage, but they need it guaranteed. They need to be able to delete a column and know that it's deleted. They want to be able to trust it. They don't want to be locked in. They want to be able to choose their query engine. So they come up with Apache Iceberg. And there really was kind of a back and forth. There was a lot of uncertainty between like Delta Lake and Iceberg over which format should you choose. Up until very recently, I'd say. I'd say 2 years ago, 2.5 years ago, I started the San Francisco and the Seattle and part of the New York Iceberg meetups, and I was begging people to come listen to Iceberg, like come talk about Iceberg. They're like, "How'd you get my number? Go away!" And nobody came. Nobody came except the Snowflake people, and they had to because it was at their office, and I made them come. So nobody cared. And then all of a sudden, what happens? Databricks acquires Tabular. Tabular has Ryan Blue and Dan Weeks and the creators of Apache Iceberg. So the creators of Delta Lake have now acquired the people who created Apache Iceberg and have vowed interoperability between the formats. So now this is a huge sigh of relief for organizations who worried about choosing the wrong one. They're like, oh, it seems like the industry has settled on Iceberg for interoperability. All of the formats have their strengths and weaknesses, but Iceberg's strength really is industry interoperability across tools, flexibility, avoiding vendor lock-in, which I would argue is going to be critical for AI. So why does all of this matter? Well, if we get back to we're struggling with AI, this is what everything looks like. You know, if you're lucky, maybe you have an open table format, but we've got the transactional systems, which are critical. We've got a bunch of different spread out analytical systems. And then we've got a data lake that nobody really uses because it's untrustworthy. So we dump some of that data back in the warehouse. And now we've got these open table formats, but they're difficult to work with and maintain. So what does this have to do with AI? Well, those 40% of AI projects that are failing fail for typically 3 reasons in my experience. 1, entity and concept ambiguity. Like they don't know what you mean by revenue. Staleness, they do know what you mean by revenue, but they found old revenue. And 3 is they just can't find it. So they don't know what you mean and they can't find anything. Well, how can we fix that? Well, if we think back to Bill Inman's single source of truth, turns out that Anthropic and MotherDuck and Neo Labs all did a study that having a single source of truth is the number one most impactful thing you can do for agents to be successful on top of your data. Well, if we look back to our nightmare of a data structure, how are we going to come to a single source of truth with all of these ETL jobs and with all of the rigidity? And now we've got agents which aren't just doing like one query to update a dashboard. You query the agent, and then the agent queries your data 200 times. So you want a lot of flexibility there. So I would argue that getting to a single source of truth and reducing a lot of these ETL jobs is to do a data lakehouse and make that the center of your flexible, open data infrastructure. In fact, OpenAI and Anthropic both have Iceberg lakehouses. So I think that speaks to that. Staleness, you want to work hard on, and I'm sure we're going to hear a lot about how to have real time and fresh data from the other folks, but you want to make sure that, hey, if there's 5 tables that all say transactions or revenue, and we all know it's more like 500, we want to know which one's most fresh. So you need to be super clear on that. So you need to have like a semantic layer, which is giving you strong definitions so that there is no question. And the third thing you can do to make agents more successful is really doing a CI/CD process with agent skills and MCPs and hooks and sub-agents, all of that. But that's way less important than having a single source of truth, which I would argue the most flexible single source of truth that you could have is a data lakehouse. Why? Because you're not locked in. So if we look back to our different components, we separated out storage with S3. You can have open file formats like Parquet. We've got Avro. We've got ORC. Vortex is coming out, but Parquet is probably the most common. So we've separated out our storage. We own that. That's ours. Then we've got our data separated out. Well, if you have Parquet, then multiple engines can read that. So we've solved that. Our metadata. If we want to own our metadata and have it free from vendor lock-in, well, this is where Iceberg comes in. Iceberg and other open table formats. But with Iceberg, you free your metadata. It's not locked into an engine. You can use DuckDB, you can use E6 data, you could use Dremio. You don't have to change anything. You don't have to do a giant migration to swap out your query engine. You own that through the metadata, which frees up your compute. So again, because the future is so unknown, there's so much volatility, there's so many possible futures, you don't want to lock yourself into past performance. If you lock yourself into one solution, you're betting that that solution is going to give you everything that you need to be successful in the future, and two, that solution will be given to you at a fair and reasonable price. And if you're locked in, maybe that won't happen, maybe it will. If you have flexibility in your data infrastructure, in your storage, your data, metadata, compute, enabled through things like Apache Iceberg, you have the flexibility to adapt your strategy because you own each part of your stack, regardless of what happens with AI in the future. So this is why I'm excited about Iceberg. This is why I'm seeing giant organizations who are implementing AI also implementing Iceberg at the same time, and why I believe it should be the center of not just your data stack, but also of your AI strategy. Thank you. I want you to know I do create slides. Some of them are actually good. We just don't use them. So feel free to get a copy of the book if you didn't scan that QR code. What's that?
Let me open up the platform for quick Q&A.
Based on your experience, which Gen AI products besides customer experience have delivered ROI? And why do you think people are not able to deliver ROI besides customer experience using all those Gen AI projects?
I don't hear very well. What was the question? What causes low ROI?
Yes, except customer experience where you feel, agents have really, because what you talked is all, people are using Lakehouse, people have moved, but still I don't see ROI across projects.
Yeah, there's a lot of reasons why there can be low ROI in an agent program. One is not defining the outcome. You don't know what the definition of done is or what the success would be. You just want to build agents to build agents. That doesn't work. You need to have a very specific business outcome. So high impact, low effort. That's the golden, hey, let's start that with our agent proof of concept. Two is not governing cost initially, which is why having the flexibility to route between query engines is important. Maybe you want the Snowflake query engine. Maybe you just want DuckDB. Maybe you need Trino to federate. You want to be able to swap between those. And then you also want to be able to swap between models. You don't need Opus 4.8 for everything. Sometimes you can just use Haiku. So you need to be able to have flexibility there in your routing. Or maybe you need hybrid inference where you have open source and proprietary. So it's really thinking through the ownership and flexibility of your agent program in order to have the outcome that you want. Awesome. That's my time. Thank you.
Any more questions? Anyone?
Yeah, somebody from IBM would be happy to answer your questions if you have them.
All right.
Awesome. Thank you.
Cool. Big round of applause. Next up, we have a talk being presented by two speakers. So more the merrier, of course. We have Amit Prabhu in black tea. He's a staff software engineer at Razer Pay, focused on building scalable data platforms and distributed systems. He has spent over 5 years at Razer Pay already, solving complex data engineering challenges at scale. Most recently, he's been leading the architecture behind their Iceberg-based Lakehouse platform. Next, we have Vishwajit, who is a senior software engineer on the data team at Razer Pay, specializing in distributed systems, real-time data processing, and stream processing at scale across Kafka, Flink, Spark, and Apache Pinit.
Yeah. Hello, everyone. This is Amit. I work as a staff engineer leading the data platform and product team at Razer Pay. Been in the tech space for about 9 years. I started my career building the enterprise softwares in the identity management domain. And then I moved to Razer Pay during the COVID times. So been 5 years at Razer Pay and part of the core data team since then. And at Razer Pay, I got to work on hard data problems, especially in the area where when you are serving data to millions of users, the problems that comes there. So be it like you are serving reports to merchants, or you are syncing data to merchants warehouse, or you're building an analytics dashboard to merchants. So these kind of problems are something I worked on from the past 5 years. So last year, we had two interesting problems related to data warehouse, where Iceberg became the part of the solution. It was the core part of the solution. And with me, I have Vishwajit, who will also cover one of the use case. And I'll start with the incremental denormalization problem. So before I start, I just want to have a quick show of hands. So how many of you have seen a denormalization problem? As in you are creating a materialized view and you are constantly worried about refreshing that view so that it is up to date and does not have much lag. Any quick show of hands? Okay. So I think there are a few people who have already come across this problem. So yeah, let's get started on the problem statement. So I'll give you a quick glimpse on the metrics that Razorpay operates at. So we have 10 million plus merchants registered with us, and Razorpay processes around 20 million plus payments per day. And we have around 6 billion plus events coming in. This includes all your CDC events, and there are click events and many other events. And this, based on the numbers, you can see that for 20 million transaction, we have 6 billion plus events. That means there is a high mutability. A payment goes through many multiple stages of status change. And with that, we have to solve the mutability problems. And also we generate around 1 million plus reports per month that accounts to around 25 to 30,000 per day. And we have a couple of critical reports which we send to regulated bodies like SEBI, BSE, banks, where the money movement actually happens. So this is a brief overview of the numbers that Razorpay operates in. And if you look at the numbers, it's clear that we are operating at a TBs of 100 TBs of data. But the problem for us is not the volume of data, but the diverse source of data. So events, these are CDC change events and also events that are happening on the dashboard and other services. Yeah. So when I say diverse source of data, we have 100 plus microservices at Razorpay. So we have one microservice for each payment type, whether it could be net banking, UPI, and many other things. Then there are microservices for each action, like settlement, adjustment, refunds, those things. So these microservices, as per the design, they have a localized database. So they store the data in their own database. And if a consumer wants to look at a holistic view of data, where he wants to see the transactional data across the databases, then it is very difficult. So that's the gap that data platform team at Razorpay builds. So it has an ingestion infrastructure where we sync the data from different services to the common lakehouse, which is set up on S3. And these events that come to the CDC, we create individual tables, as in these are replicated tables of the microservice databases. So here the problem does not solve. So we still have the individual tables and still we have to do the joins. So consider a use case where you are rejoining the same entities again and again. So it would be very inefficient if you run a query as in you join the entities at a runtime. Instead, a common pattern that everyone follows is creating a warehouse table. So you create a denormalized table. When I say denormalized, it's a flat white table that has data of all the entities that you join. So these entities we pick based on the domain, like for the customer is interested in. For example, a consumer wants to look at all the data points for a payment. So we join payment, cards, orders, discounts. So these are the entry points that we join in and we create a wide denormalized table. So we call this denormalized table a fact. So this could be slightly different from what the industry norm is, as in internally we call it a fact that it's a white table on S3, which is created by joining 10 to 30 databases, the database tables. And these are materialized so that when you make a query, we don't run the query at runtime. So it's just a select clause with some filters and you get the results in a faster time. So how do we generate these facts? So this is the initial setup we had a few years back. So we have a simple setup. There is a Airflow DAG, which triggers a EMR job, a Spark job. It reads a configuration file on S3. The configuration file contains the tables that we need to join and the columns to be selected. And this Spark job queries the data from the lake, brings in all the data, creates one white table, and then it upserts that data on S3. So this is a very simple setup. And then this job also publishes the checkpoint to the downstream services so that they can decide what to do. As in, for example, in reporting service, we cannot serve stale data to merchants. It has to be real time. So since the facts have a lag of maybe 24 to 48 hours, so we need to serve some data from the real-time store, which is TiDB here. So we call it a warm store that it has data up to, I think, 3 to 6 months of data. And this also has an ingestion setup where data from different microservices flow to TiDB. And reporting service reads part of the data from facts and part of the data from TiDB to serve reports to merchants. Yeah, the kind of queries that we run, right, where we are joining 10 to 15 tables. So TiDB was more efficient in that terms. Yeah. Yeah, latency. Yeah, and also cost effective. So what are the challenges with the monolithic way of generating facts? So one problem is unbounded joins. So at Razorpay, in the domain itself, so we have backdated references. So consider a payment. So you are making a payment on an order which could be created 2 or 3 years back. So you don't know what is the filter to put on orders. Suppose you are joining payments and orders. So you can put a filter on payments, but you don't know what filters to put on orders. So problem with that is you have to do a full table scan on orders. So that is the unbounded joins problem. So we don't know the kind of filters to be put for the secondary tables. So that involves all the full table scans. So now, since there is a full table scan, this whole job runs for very long hours. So we have around 50 plus facts, and that takes around 70 plus compute hours on EMR per day. And there are some jobs which run for 9 to 10 hours. And these are very large clusters, like 4x large clusters with 10 to 15 nodes. And this is like a lot of compute goes into those generating those facts. Now, there is another problem with long-running jobs, which is spot loss. So we cannot run these jobs on on-demand nodes. So we run it on spot nodes. But since these are long-running, so the spot loss is inevitable. And whenever the jobs crash, it has to start from scratch because we are doing a full refresh here and not intermediate checkpoints. And the last problem is the joins on the data lake is very expensive because I talked about the unbounded joins. So if we have to do the joins at the runtime, when a report is requested, let's say you want to join part of the data from fact and part of the data directly from the lake, it is difficult because you have to do a full table scan. And that would increase the latency of report generation. So these were the problems we started facing with the old way of generation. And we tried a couple of attempts. We tried decomposing the fact into smaller facts. So we created small sub-facts and then chained into a larger fact. And we also tried reducing the retention and falling back to alternative source. But none of them significantly reduced anything, as in there was a marginal improvement in the cost and other things. And we also tried one long-term solution where we introduced the streaming ingestion, where the pipeline will subscribe to the topics of the tables, which it needs to denormalize. And then it will do a stream join. And if some of the joins are missing in the stream join, it will do a lookup in the TiDB. So here the problem is, since we have a backdated reference, right, as I was saying before, so I need all data in the TiDB. Because if an order is created 5 years back, I would need all data in the TiDB so that lookups can be done. So this made us put all the data in one store, which was not a cost-efficient solution. And then we have high mutability. We used to get around 10 million events in a 30-minute window. And we were reprocessing a lot of data again and again because a payment goes through multiple stages of changes, and that creates a lot of mutability. And another problem is write amplification. So consider an example of payment link. So with single payment link, you can make lakhs of payments. And suppose you have created a denormalized table where payments is your primary table and you are doing a left join with payment links. And suppose some attribute changes on the payment link. Now you have to find all those payments which are linked to the payment link, and then you have to update those rows. So this is a write amplification where a single change on payment link, you have to scan all the data on payments and update it. So these were the problems with streaming ingestion. And then we had to think of an alternative solution. That was an attempt. Yeah. So far we were clear that we have to do some kind of a incremental processing. So we cannot do a complete refresh of the materialized view every day because of so much of problems. And when we thought about this, one approach was, what if we treat facts as maintainable graph? When I say graph, consider a real world scenario, like you have a payment which you are making through card, and then which is happening on an order, and then you are using the offer with a discount. So this real world relationship can be represented as a graph, and this graph can help us identify what changes to make when a change event comes on the any of the node. So this was the idea behind incremental facts. I'll go over the traversal in the coming slides, but this required us to answer 3 questions. So how do we get update events for any of the entities? So that's the first question. And so what we did is we created a pipeline that will ingest the data partitioned on updated date. And so that if I want to get yesterday's changes, I can directly go to that partition and fetch the latest changes. So next is how do we identify the related rows? So that is through the graph. And then how do we look up efficiently? So this was the problem where we needed some kind of indexing on data lake. So what we did is we created a mini table. So this mini table contains only the join columns and the partition values. So for example, if you consider payment index, it has ID, order ID, card ID, and created date. But actual payment table has 30 plus columns. So we created a mini subset of subset table that contains a mapping of ID to partition, because in Razer Pay, all the data is partitioned on created date, which is how different consumers query it. And then using that index, we can speed up the lookups. For example, if you want to find out details about a payment ID X, so what you can do is first you look up in the payment index with that ID. So you get a list of partition values. You get the distinct set of partition values and then pass it in the lookup filter. So that way, when you are doing a lookup, you can directly go to a particular partition instead of doing a full table scan. So this was the solution which helped us to reduce the retention on the warm store. So earlier, we had to put a lot of data in the warm store because of the lookup efficiency. But with the secondary index, we were able to do lookups on the lake itself. And the solution became very efficient. So coming to the graph traversal, I'll quickly go through this. So we broadly classify the flow into 2 flows, primary flow and secondary flow. In the primary flow, we process only the primary table in the fact. So here, consider I have created a denormalized table with these entities, payments, cards, orders, transfers, and settlements. Now, I get the updates for payments through the updates table. Then I start doing a lookup for each cards, orders, transfers using the secondary index. Once I get the data for all the entities, I create a denormalized row, which I will assert on the Iceberg table. So with this, whenever a change comes on payment, I know which data to look up. So why do we need graph? Because if you are finding data of settlement, you cannot directly go from payment to settlement. You need that order, which is a topological sort where first you have to go from payments to transfers and from transfers to settlements. So the graph was solving that problem for us, where in which order we have to look up so that we can create a denormalized row. Yeah. No, these are happening at a pre-computation time. These are not at the report generation time. I'll come with the numbers on that. Yeah. So if you look at the most databases, they stop at the primary flow. If you look at ClickHouse or DBT or any other flow, they refresh your materialized view, but only for the primary table changes. So we had to solve the secondary table changes as well. Consider an example, you made a payment. Now, the payment comes from customer to the Razorpay nodal account. Now, there is a settlement action where we transfer the money from Razorpay account to the merchant's account. So this settlement always happens like maybe on the same day as payment, or it can be a week after the payment. So if the payment is created and later the UTR of the settlement is updated, so it's an independent event. There is nothing relation to the payment. Like there won't be any change events on the payment, but only event change will happen on the settlements. So that's why we had to solve the secondary flow. So what we do is when a change event comes on the settlements, we fetch all the previous day updates of the settlement. Then we do the backward traversal. We first fetch the transfers and then fetch the payments so that we get the primary ID and the date. So reason for doing this is when you are inserting data into a fact in Iceberg, right? You need to pass the partition values. Otherwise, Iceberg will do a full table scan, right? So that's why in order to limit the partition that are touched during the upsert, what we did is we do a backward traversal to get the partition dates, and then we pass that in the merge condition to solve the secondary flow. So why did we use Iceberg? So there was one final piece of the puzzle where we had to do a runtime join because we cannot put all the tables in a fact. Like the example I told you earlier, you have a payment link which can link to lakhs of payments. So if the payment links gets updated, so you cannot, if the payment link gets updated, you will have to go to all the payments and update the property. So instead of that, we thought of separating that out. And we wanted a common predicate to be pushed. So if we are joining payments and payment links, we need some column to be common to both payments and payment links so that we can push the predicate and we can scan less amount of data. So we thought of doing a bucketing, which Iceberg supports. So the advantage of this is most of the reports that we generate are on merchant ID. So if I create a bucket on merchant ID and if I do a join, so the predicate pushdown happens and it will scan only that merchant's data. It can scan other merchants' data as well, but still the amount of files that it scans would be very limited. So we also did further optimization. We added sorting so that within a bucket, you can further prune the files that are inside. And with these changes, we were able to get down the data scans to less than 35 GB, which was doing a full table scan. And also we use the position deletes and MOR feature that Iceberg gives, which was able to reduce the write speeds during incremental denormalization. And also scale, Iceberg was able to scale well with its efficient metadata pruning as the scale advanced. I'll just quickly show you the numbers. So after we migrated our facts to incremental strategy, the cost dropped like 90%. And these are some of the facts that we moved it to incremental strategy. And if you could see that earlier it was taking 30 plus hours, that got reduced to less than 3 hours. And one of the largest fact, which was taking 8 hours, got reduced to 1 hour. And we were also able to reduce the scan window on TiDB because the incremental fact would run daily and it would have a consistent data. So we didn't have to fall back on TiDB. And also with incremental fact, we were able to support the data since 2018, which is Razorpay's starting date. And this was the approach to make the facts scalable to Razorpay scale. Yeah, up next, I'll hand it over to Vishwajit, who will cover a streaming analytics problem.
Thank you, Amit. Basically, what Amit covered was the problem statement that we covered with the batch solution. Now, I will guide you folks to the problem statement. Other problem statement which we had is that what if your merchant comes to you and say that they want the analytics to measure in the real time? So then that batch solution won't work to you. Then we move it. Then another solution where basically which we went to the near real time solution. But earlier, prior to that, we had a batch solution also to that, which was actually doing a full refresh, scanning over some 10 terabytes of data, and which was giving us some freshness of T-1 day. But suppose you are a merchant, you're landing on a Razer dashboard, and you want to see metrics in real time, and you just see that the freshness of data that you're seeing in the dashboard is available till yesterday midnight or 1 a.m. or 2 a.m. in the morning. But that's a problem for you. Sorry, that's a problem for you because when a merchant is going to see the business growing in the in the real time, they want to track the metrics also in the real time, be it like funnel metrics, GMVs, or the payment drop-offs and all those things. So we have to tackle those things in real time. So then we move ahead with the solution of a real time, where we chose the event stream basically with the help of Spark, and we coupled it with this Iceberg. And we obviously, when you go with this thing that you serve a high QPS analytical use case, you think of a OLAP. But we didn't move to OLAP because we wanted a low-level control over full absurd semantics. And we had multiple challenges, like we need to ingest from multiple Kafka topics, which are related, we share the context. And when you go with this multiple topic ingestion and all, you always come up with this later I will need out of order arrivals of events. And thus we didn't went ahead with OLAP, and we built our whole pipeline of this Spark plus Iceberg, which we give us to this complete absurd semantic and all those challenges. Yeah, thank you. So just a complete overall architecture of the pipeline that we had. Yeah. We have the multiple Kafka topics, and we have this Spark job configured for each of the use cases, and the Spark jobs is completely config driven. It can ingest from many topics. It can do in-batch coalescing, aggregation, dedupe, many things that we do in general absurd. And then after that, we dump it on our Iceberg, basically our data lake S3, and then from there, the Trino is getting utilized to serve the merchant dashboard analytics. And the features that we actually leveraged with the help of Iceberg was this hidden partitioning, bucketing, Bloom filters, and merge and read. We can go. Yep. Whenever you go with the streaming solution with Iceberg, the main problem that comes up gradually is the small file problems. With any stream processing solution, you get it. But over the, I think, plenty of couple of weeks, when we started this job, we already had this compaction job at the background. And we found that the compaction job is not working out because the small file problems are compiling up. It went ahead to some odd 200K small files. And the main root cause why the compaction got skipped silently is we had this target file size of the Parquet is 512 MBs, and because we had this partitioning and hidden partitioning and the bucketing on solution, each partition only holding some 19 MBs of data, and that's it. So whenever the bin pack was trying to compact those files, it was skipping it because it was finding it out that the cost of IO, converting those 270 files into one single 90 MB file, something like that, it's too much to save it. So it was skipping it silently and without giving you any error. So your compaction job is running finally perfectly fine. Your streaming job is lagging behind. Your processing time is increased. You're putting a lot more resources, but nothing is working out. So then we just set on it and just figured out that, okay, this is the problem. Then we reduced this target file size, which was, we reduced to the 32 MB something, matching to our volume. And then we also pivoted that we don't touch the active hot partitions that we have. And basically we are touching only those partitions, T-1 partitions that we have to compact. And then obviously, ultimately after that, you verify that the snapshot is working fine. You check the logs, you verify the operations that, okay, it's replacing things and all, so that it can compact. Yeah, those results that we got from the streaming solutions, that earlier we had a freshness of T-1 day. Right now we have a freshness of 5 minutes. And the accuracy also is 4 nines, and it also helps us, the compaction also helps us in reducing the cost of compute by 10x. And for each other pipeline, we almost saved around some odd $1,000 on per month. And the few compaction also solution compacting this smaller file problems are 200K to some 1,500 files. And with this cost we saved, we also increased the retention from 30 days to some 3 months. Yeah. So the major lessons that we learned across both of the use cases, be it batch, be it stream, that streaming is not always the correct solution for you. So in case of Amit's solution, it was a different solution where you need to have a older lookups. You have to look up in TiDB and different external sources where you cannot do streaming solutions as usual. But whenever it comes to the real-time use cases, I don't. The use case that I was solving was not having any external lookups or older data lookups and all of it. It's just like that. You have to join multiple topics or multiple streams in it, and then after that you can go with it, and that works perfectly fine for us. So whenever you're choosing a streaming solutions, choose it very wisely. You cannot go blindly for a streaming solution or on any problem statement. Yeah, the data that we have on Lake cannot be just sitting like an archival state. We have to make it queryable. And for that, we have leveraged different indexing layouts and all those things that helps us in querying data directly from lakehouse rather than going directly to different silos like TiDBs and other places. The layer choices is a very major cost driver. You cannot go silently on this. If you choose correct layouts like ordering, bucketing, indexing, and all those things, it will help you also reduce the cost and also the query compute time. Yeah, sure. And obviously, if you're choosing a bin pack compaction solution for your Iceberg streaming solution, just check it. You cannot run it and just ignore it. You have to verify that it's doing it perfectly fine based on the volume and partition size that you have. That's ahead of this, whatever we have built, in the future, we are going to make the secondary index in a real-time pipeline, and also to extend our incremental processing to different silos, be it TiDB or different data stores. And obviously, the streaming solution that we have, we are thinking to make it generalized because whatever event stream system that we have, events and CDC, all those pipelines. Thank you. Last part, streaming, make it come. You go back. Yeah. So this we solved for one of the product we call checkout. So we are planning to get it to different products and all the use cases that we have across Razer to onboard on the same platform where they can stream the event data into Iceberg directly in a real time mode. The job is the pipeline is very configurable, so you just need to onboard a config on it, and then it's done.
With high concurrency, right? So there is. So are you using Spark streaming?
Yeah, we are using Spark.
So how do you handle the commit conflict? So there, at high concurrency rates, so we have faced a lot of commit conflicts, right? When the concurrency is so high, how do you handle that?
Basically, we didn't face any issue till now but if you see that we have this batch of 5 minutes, it's deliberate because of the use case. So whenever we are committing, we just doing it, coalescing and all those things. We never faced any issue related, if you're saying about S3 or even related to on the side of Iceberg. We haven't faced it, but I'm not sure.
Have you seen any race condition on metadata access when you're ingesting a lot?
No.
So you said that you have 5 minutes of batch, right? So are you creating micro batches of 5 minutes or dumping the data into your data lakehouse in 5 minutes?
No. We the whole 5-minute window is collecting the data from the sources, and then after doing some internal processing, then they dump it to S3 and Iceberg.
Okay, so after the 5-minute processing, it dumps to Kafka itself.
Yeah,
right?
Not Kafka to S3.
Okay. So so how you're holding that, right? So are you creating in your Spark configuration, you're setting the 5 minutes or?
In your Spark configuration, we're setting it to 5 minutes.
Thank you.
Yeah, event first.
So like you mentioned that you reduced the target file size to 32 MB, right? For greater compaction, right?
I'm not able to hear you. Can you just speak a little?
Hello. Yeah. So you mentioned that you reduced the target file size to 32 MB, right? For greater compaction.
Yeah.
So like in such a scenario, like Iceberg by default supports file pruning, it is known.
Mhm.
But want to like get better performance if it also support the dynamic file pruning, right? So are you housing your in-house Iceberg with enhancements of your own, or like are you relying on the open source?
No, we are relying on the open source. We didn't went that way because of the certain limitations that we had of the use case, because we want to FAD on the real-time versus you don't want to corrupt the metadata also.
Okay. So by default, it is 512. Like any challenges you faced with 32 MB, like we faced, so we moved to 128.
Yeah.
So
So
like,
it was mentioned also that it depends on the volume of the partition that you have.
Okay.
Each of the partition that you have, based on that, you can configure it.
okay. Fine. Thank you.
And one more thing to add is, I think we were doing copy on write. So I think the use case itself was like that, where we could not do a MOR because of the real-time constraint. So I think having a smaller file size helped us there. So it depends on, yeah.
Hi. To maintain the order and payments and settlement linkages, right? You told about one graph. So are you using any graph DB or it's like in-memory store?
No, so data is not in the graph. I think, we are using the graph only to identify the order in which to look up the data. So data is not in the graph. So we don't use any graph DB or anything. So dependency graph is just for us to traverse and identify when a change comes, what all data I need. So it serves as a blueprint for us to look up the data.
So it's just like a ID linkages between the tables.
Yeah, it's a link. Like based on the join conditions, we
Yeah.
create that graph and we traverse it to identify the changes.
Got it. Thanks.
Folks, do we have more questions? Can I just request you all to hold until the networking section? I just have a very hard stop, if it is okay. Okay. Please hold on to your questions until the networking section. Speakers will be available and then you can discuss at length. All right. Again, thank you so much, Amit and Vishwajit. Let me just, yeah. So we are done with two good talks. Let me quickly change or switch the context for just a couple of minutes. I have Rajat with me, who is the founding engineer at E6 Data. Very quick, small plugin. He just wanted to talk about what E6 Data is for you, so that you have a better understanding about it.
Hey, thanks. A brief introduction about myself. I'm Rajat. I'm part of founding team at E6 Data. I head the data engineering solutions and I'm part of the product team at E6. So what do we do at E6 is we have heard about a lot of problems right now, like from the previous talk, right? Our team from Razer had explained their problem with respect to streaming ingestion or the querying aspect from the concurrency and everything, right? Okay. Those things are handled very easily by E6 Data. When I say that, we handle, whenever you talk about any compute engine, right? Or a query engine, similar to what Trino in one of the previous example, which Razer guys showed us, Trino or Databricks SQL Warehouse, Photon engine, and all those things. That is where we come along. We are a Lakehouse native compute engine. So the problem with any real-time scenario or workspace is a lot of concurrency will be coming into the system. How do you handle that? Of course, engines like Trino, Databricks, Snowflake, definitely they are going to handle it. But one more important aspect for any of these components is the cost. Cost is if you pay it, you will get a lot. But nowadays, it's like I need cost benefit as well. Along with that, I need to handle the SLAs of the end users as well. How am I going to do that? That is where E6 comes into the picture. We handle high concurrency load at a very cost-effective thing. And that's where you can see over there, our tagline is like save 60% of the cost saving. You don't need to migrate any data from your Databricks environment or your Snowflake environment or Redshift environment. They have the capability of, writing the data into Iceberg or Delta or querying it from there. We connect to that particular catalog, be it Unity catalog or be it Polaris catalog, be it any catalog, we connect to that. And the data format, it could be any data format. It could be Iceberg, Delta, Hoodie, plain Parquet, anything is possible. And coming to the data storage aspect of it, or the where exactly your data resides, it could be on cloud storage or on-prem as well. Engines like these, like for example, Databricks or Snowflake, they cannot be deployed on any on-prem databases or on-prem solutions, right? So E6 Data can be deployed over there as well. So it's like hybrid architecture. You can use E6 Data for any querying purpose. And one more product which we have is the streaming engine. We have heard problems about that. Certain streaming engines will not be able to handle so and so loads. For example, let's take an example of a security organization or an observability tool, right? Where you will have millions of data coming every minute. That could be 100 or 200K events per second. which system is going to handle that? There will be a data loss every time. This is where our streaming ingestion will come into the picture, which we have built from grounds up. We handle 100, 200K events per second without any data loss and allow you to query within seconds. And it's not we are not using any proprietary data format here. We are writing the data into Iceberg or Delta, be it whatever data format you want, and we allow you to query at high performant querying layer. So this is what E6 data is all about. Happy to discuss with any of you on how it works, how can we give it a try and everything. Happy to demo it and everything. Thank you. Yeah. The mode of E6 data in the next 3 years is to be bigger than Databricks. That's what I mean. How in Databricks, what is they are talking about? They are talking about AI workloads being the ontology or the Genia and everything, right? See, that's a play, of course. Is it solving all the problem? There is a lot of problems and every step, right? They're introducing a radon engine. Again, they're promising 10 milliseconds querying problem, right? But are they writing into storage layer? No, they're taking from Kafka and writing into Kafka again. But our promise is we are writing into storage. You can share with any people you want. You can query it as it is from the storage layer. That's our main mode. Okay. So basically, how are we going to handle any workloads, right? We don't do any heavy GC operations. We have built everything from grounds up. Any product which we have built is from grounds up. So we have control over every component within the engine. Like for example, in an engine, there would be multiple components, be it planner, be it queue management, be it executor, and so on. So, right? We have the capability to scale each and every component. We don't scale all the components and increase your cost at any given point of time. We automatically scale each component whenever it's required. So that's where you have a lot of resources free, and we work very efficiently and fast. Absolutely, we can do that. Yeah. Thank you.
Until what time will you be on? All right. Okay. Thank you so much, Rajit. He has got some other commitments, so he'll be around for another 30 minutes. If anyone wish to talk and have a much more deeper interaction, you can just ask him to step outside the cafeteria, have a word, and then, yeah. All right. So we have, coming back to talks, we have another talk being presented by 2 speakers. Both of them are Clouderans. We have Akshat Mathur and Ram Pradeep. Akshat is a senior product manager at Cloudera with nearly a decade of experience across data engineering, distributed systems, and product strategy. He currently focuses on Cloudera's data lakehouse strategy. He's driving products and capabilities around Apache Iceberg, REST catalog, data sharing, and open lakehouse interoperability. Earlier in his career, Akshat contributed to open source projects, including Apache Hive, Apache Tez, and helped build robust data infrastructure for enterprise scale data platforms. So if anyone is looking to get started on his or her open source journey, I think he's the guy. Along with him, we also have Ram Pradeep, who is a senior solution architect at Cloudera with 15 plus years of experience in building PB scale data platforms for some of the largest enterprises of India like SBI, NSE, BOB, Bank of Baroda, Reliance, Vodafone, etc. And he's extensively working with Cloudera Stack for past 10 years. He currently drives tech sales in West region and Bangladesh. So if anyone is into that domain, wish to have some more insights, he's the guy for you. All right, over to you guys. You need 2 mic?
Thank you. Yeah. Hi, everyone. So thank you so much for joining us. And we had some great sessions, so I'll try to carry the weight there as well. So today, so generally when I talk, right, I just don't want to talk about the features. I want to talk about how our customers or generally, right, those features can be leveraged in a business use case. So that's what we're trying to present today. So we have a telco use case that we want to talk about where we faced large amount of data and how we handled the data and the query performance at the same time, right? So to set the context, right? So we'll talk about the problem first, set the context, give you the understanding of the scale of the problem itself. Then we talk about the breaking point on why things break at such large scales. And then the decision matrix, right? What decisions a customer takes when they hit these sort of problems, basically the solution, right? And then we talk about the capabilities that matters to customers, the execution of that, basically the architecture, the best practice, and then the outcome, right? What was the success impact for that customer? So with me, I have Ram, who has actually been on the field and on the ground with the customer, talk about the problem itself.
Thank you, Akshat. I want you all to imagine you using your mobile phones, right? Day in, day out. I'm pretty sure you use WhatsApp. Most of you are on Instagram. You look at Facebook, and you even look at many websites, your office work, your personal calls, a lot of this stuff. Have you ever imagined everything that you do is creating data, right? Not just for you, but for telecom companies, right? And imagine a country with 1.4 billion population with free 5G, right? That's the problem we are looking at. Now, why did I share this particular context is because by regulation, every telecom company has to store this information for a period of 2 years. And every time you visit a web page, you create a record. And that record captures, again, be careful. But that record particularly captures your mobile number, your IMEI, from where you are making this particular connection, what is your transfer IP, what's your destination IP. Now, you also have to understand why they do it, right? When something happens in the context of security, in the context of crime, investigation, there is a concept in telecom industry called LIM, Lawful Interception Monitoring. Basically, what it means is the DOT is allowing the telecom companies to track and record, store this information so that whenever a law enforcement agency goes to that particular telecom and then says, this guy, I want whatever he has done in the last 3 months, right? So that is what they want to do. Now, that's the problem that we are trying to solve. The telecom is one of the largest. Obviously, we have 3. So one of the largest. All 3 are large for us. They have more than 20% market share, 200 plus million active subscribers, and they have merged. I think you know the name. So when we started with this problem, we were not just solving this particular data problem, right? We are also solving a lot more bigger problems in terms of merging 2 large telecom service providers into a single platform, different processes involved, different way of ingestions involved, different technologies involved, like bringing them onto a single platform and then making it work at the scale at which this is working. That was the challenge that we had, right? That is the true challenge that we had. Can we go to the next one? So while we were solving this problem, the biggest hurdle that we had was solving it at scale, right? Because I can always run a query, but when I'm running a query for a day, when the day particularly means 100 terabyte, right? That is the amount of data that this telecom generates per day for an IP data record. Now, what's an IP data record? The use case that I mentioned. Every time you visit it, there is a data record created, and every time every person is doing it across like the regions, it has to be collected, stored in a central location, and it has to be readily available because they will not wait. The law enforcement agency will come and then say, give me the data, and they have an SLA for it, right? If it is an internal use case, for example, let's say you want your marketing team to have data, right? And marketing team comes to you and then say, give me this data. And you will say, okay, I'll give it to you, right? And then let's say you got delayed by 12 hours, you got delayed by a day, 2 days, 3 days. The max to max that can happen is they can escalate it to your manager, maybe your manager's manager, maybe director, to the VP, maybe it will go to the CEO. cannot go beyond that. But if this doesn't go out, what happens is the CTO or the CIO will be called to the ministry's office. Right? So this is far more critical for them to solve than their internal problems, because this actually means there are legal actions, there are penalties, and this use case doesn't generate any revenue for telecom companies, right? So it's like you're spending so much to solve a problem where you make zero money, right? That's the problem we were trying to solve. So you want to take this? Yeah.
So, as Ram mentioned, right, the challenge is not just solving internal problems, but so if you think about data strategies in general, so you can divide data strategies into two pieces, right? One is your defensive data strategy, one is your offensive data strategy. Offensive is when you were trying to get value out of your data. Defensive is when you're trying to save yourself, right? So this use case is more on the defensive data strategy, on how you build a data platform layer that can save you from any replication that Ram also mentioned, right? So with this particular use case, the challenge is not just scale of data, but the nature of the data itself, the fields, the columns that you collect from the data. Now, because you have, so let me talk about the technical challenges, and then we talk about how that impacts the business, right? So there are multiple OEM vendors. There, like, you're getting the data from so many sources that it's difficult to manage it in a single schema processing, right? Then you have different files, different deliveries, and all those things. Now, the impact for that is that, as I said earlier, that the way you collect your data and the way you store your data is really, really important. You can miss your SLAs if you actually just you have a bad architecture, right? It's a time windowed SLA, as Ram mentioned, that if you miss that SLA, you're being called into the ministry. So this is really, really critical use case where you're trying to solve. And yeah. So I think we can go to the next one. Yeah. So the business constraint on this, right, is trust. That with the merger, they wanted to create a single source of truth for all their data, so they can serve the truthful data. Not so. If you imagine there are two different companies, right? Now they're merging together. If some data is here and some data is there, and the ministry comes and say, okay, give me data for this particular person, and you thought that, okay, I'm giving the data, but that is actually not the complete data. You're giving a piece of that data to the law authorities, and that's also a problem, right? So you want to make sure that the data is trusted, governed, and a unified source of truth, right? Then comes the compliance. You need to make sure that the data is being retained. What if there's a disaster, right? So you need to ensure there's a disaster recovery, and there's obviously economics behind it. You need to make sure that the data gravity is maintained, reliability of that data, and the query processing. So when we started this project, I think the query time was around 72 hours, right? So the query time for that data, let's say if tomorrow a law authority comes and asks the company that okay, I need this person's data, they used to take 72 hours almost to respond, right? And that might breach SLA even if like it's 1 hour or even half an hour, right? So meeting the SLA and making sure that the architecture that you have created or the platform that you have created is predictable every time. It should not be like, okay, today my query is running for 17 hours and then tomorrow it's suddenly 72 hours, right? So mapping it to technical constraint is that scale without partition explosion, schema evolution as the business grows, right? So today you might be collecting this set of data, but tomorrow government comes and say that, okay, I need to also collect this particular data, which you were not collecting today. So schema evolution was also one of the key part of this architectural requirement. And that's where Iceberg comes into play, right? Now we'll talk about the technology a little bit more. So do you want to go next?
So, so there are the LIM use case typically covers multiple aspects. It covers your call data records, SMS, voicemails, also the IP data records. Now, this particular use case, we are predominantly concentrating on IP data as a use case because that is the larger scale. Imagine generating 1 trillion records a day, right? And then by nature, you have to ingest them live because you can't wait for the end of the day to load all this information. There are requests coming in as we speak for some of these things. Let's say there is some attack going on in Kashmir or on the border. The requests are flowing in already. They want to find out who is talking to who. They want to find out which IP is being visited by whom. So this information is coming at you with full speed at a very higher volume than you generally expect, right? Now, imagine we all know stock market. National Stock Exchange being one of the largest derivative in the country or in the across the globe, actually speaking, by transactions, they generate around 20 billion records a day, right? That is huge. And during the market time, we actually ingest around 1 million records per second. Here we are talking about 1 trillion records a day, right? Imagine at what scale we should be doing it. And this is directly involved or directly impacting national security. So the precision is also equally important. Otherwise, let's say you are losing some data that could actually trigger a national level event. So both of them had to go hand in hand. Some other technical constraints before we go here is that there are millions of phone numbers, millions and millions of IMEI numbers, millions of IP addresses. You can't partition them by any of these dimensions, because the moment you do this, you're over partitioning it, right? And when someone gives you 2 metrics to query, you're done. That query will never go through, right? So we need to understand what are the query patterns, which dimensions are being queried, and the dimensions keep changing, right? So they keep moving as it's a moving target. Today it's IP, tomorrow it's IMEI number, at some point in time it's something else. So we have to architect for growth, architect for change. So that is why the table format of Iceberg is the best, because we can't go back and change 10 petabytes of data for a new partition schema. It's not possible, right? You can't go back. See, every month we are talking about 5 to 6 petabyte. Now, after a year, you are saying my partition schema has to change. I can't go back and edit 30 petabytes of data to come fit into the new schema. It's impossible for us to do. And it's too costly for me to take this use case to public cloud, because the storage costs, and every day I'm scanning so much data, and they can ask any period of the 24 months. So it's economically not reasonable for us to take it to cloud, right? So that's why we had to choose an on-prem solution, a stack which gives you lowest cost per density, a stack which gives you the most possible performance. We have evaluated multiple engines. Trust me, so many queries were run with different engines. We tried Hive, we tried Spark, we tried different other engines. And ultimately, the customer stuck with Impala. They said, this is the best engine that is giving me the fastest response on Iceberg, right? So again, the technical concepts of why we chose Iceberg are there. I don't have to tell you that these are the things that are needed. The use case itself is driving towards Iceberg. Can we go to the next one?
Folks at the back, if I please may request you all to take the conversations outside the door. Just it will allow us to have a good attendee experience. Thank you.
No, no, there is real time. So you have to understand the use case that we see from a end user perspective, from a retail perspective, are completely different from what they are doing. So if you look at how, again, we are deviating, but I'll just take 2 minutes and we can speak later. So as a regulator, SEBI has certain guidelines over how things have to go. So there is a concept of orders and there is a concept of trades in stock exchange. So when you place an order as a retail investor, and when I place, let's say you place a buy order, I place a sell order. When these two match, it's a trade, right? Now, if there are too many buy orders and there are no sell orders, or maybe the buy prices are too high, it can actually impact the stock price. So these things are to be monitored live, and they actually have to send some information like order to trade ratio. There are other concepts that they have to send out every 5-10 minutes, so that they capture how the market is moving and if it is moving because of certain people or certain organizations. So this is a real use case where your data is coming in and you have to immediately start reporting on top of it. While end of the day reporting comes next day morning, that is typically for retail investors to see, but from a regulatory standpoint, everything happens live, right? So what worked for us, I'm going to cover this slide and hand it over. So what worked for us at this particular customer, largely speaking, is obviously we had to do a lot of tuning on the storage layer. We used a combination of HDFS and Apache Ozone. So we had to look at how the name node performs, RPCs, the file sizes? How do you ensure the Parquet indexing is being used? And how do we ensure we are not reading the unnecessary files? And what dimensions to sort it based on? So Z-order sorting, I think, is the most impactful, meaningful feature that has helped us achieve this particular use case in this particular scenario. And we used multi-dimension sorting here because your where clauses keep changing. So, right, you can't have, I cannot just filter them on mobile number and say I'm done with it. Because tomorrow they might ask me IP address based, they might ask me IMEI based, they might ask me transfer IP based. So, and sometimes they have a combination. Tell me all these mobile numbers or all these dates with all these IP addresses as the target, right? They will also say, this is a source IP, this is a target IP. Give me the list of mobile numbers or IMEI numbers who visited this particular period, right? So those kind of queries will come and it's not going to be done with a single dimension sorting. So that's why we had to go with Z-order. And even though it comes at a cost, because Z-order sorting is not going to be easy, especially when you're doing it at this scale. So we do it partition by partition every day. And this takes some time. But that time is worth it because this is a one-time job. Once you're done with this, you don't have to touch that partition again, at least for a foreseeable future, right? So with that, do you, I mean,
You can talk. So one thing that I want to talk about Z-order is like it's not for every use case, right? Let me put it very frankly out there. So there is a trade-off. So in some cases, lexical sort is the best, right? But if you have multi-dimensional high cardinality identifiers, right, then it's better if you do Z-order sorting. It is costlier, but when you query the data, like it gives you much better performance as you can see, right? That's what we were able to achieve at this scale, especially for this use case. So before using in technology, one thing we have to always map to is what we are solving for, right? And the thing that we were solving for here is the high cardinality multi-identifier, where Z-order really made sense, right? Because if you partition by just one thing, right? Let's say you partition by timestamp, so your law and order does not ask for a time range, right? They're asking for more. They are asking for more subscriber ID, right? Private, public IP addresses, and that's when you sort for the Z order. And the key benefit, this is the best fit conditions are mentioned there. I wanted to give more information on this slide so everyone can take pictures. But reality is that when you have low correlation between these identifier, you should think about Z order. When you have selective queries, right, where you want to skip the data, so like reading the data, skipping the data is more important than reading the data. That's when you think about this, right? So the bottom line that I want to leave you with is that Z order is great, right? But it does not imply for everything. Sometimes lexical order is the best for the use case, but always think about the use case before you think about the sorting mechanism. So in this particular diagram, right, I wanted to cover the general ecosystem of an enterprise. If you see, like there's not just one particular technology here. There are multiple, right? And this represents overall architecture of an enterprise, any enterprise for that sake. So they have ingestion, they have processing, and they have consumptions, right? And I think this is where openness really comes in, right? The platform needs to be open because these days any company is trying to be multi-vendor. They don't want to be logged in. They want to make sure that they are open, they are accessible by any other team that they have, right? So we have a lot of use cases. One was obviously the scale. Scale was the problem, right? Then the problem was how this data is being accessed or leveraged by different departments of the same organization. Now you can say that, okay, so let's say if you have an organization of 100,000 employees, right, not customers. So can you say that, okay, in the entire company, I will use only one product or one vendor? That's not true, right? Every team wants to use the tool that is best for them. And that's the reason why I love Iceberg, because it's truly open, or at least give you the ability to be open. And that's where you see we have streaming ingestion, data in motion, data engineering, all dumping the data into a lakehouse, right, in your Iceberg. And then you have REST catalog or data sharing like capabilities. So you can expose that data with the same platform or to other teams which might be using other platforms like Snowflake, Databricks, EMR, Athena, right? So the reason why I always like to talk about this slide is when you think about your platform, always think about how you can expand the use cases for that platform and expand the usability of that platform rather than just locking in into one particular platform. And I think that's where most of the companies are going in that direction, right? But with Iceberg, that's the beauty. You can be open because it's an open standard. With REST catalog, you're getting open standards for accessing that data. So we don't want to go next. So we do have some reference implementation on how we did that for the customer. I'll let Ram cover this slide. But before we go into the implementation, this is very high level, obviously. So we already talked about Z-order sorting, right? And this is just the building blocks of those on how these different OEM files comes to the landing zone, and then we use Iceberg. So do you want to talk about the hot and cold specifically? Yeah.
So I'll just take a couple of minutes and we are done. So how this happens is they have multiple OEMs. Obviously, it being a telecom provider, you have TARs in every place, and every TAR has a different manufacturer, a different networking operator. So the formats come in different ways. So the first thing that we have to do is bring that data in one place and then standardize them and then keep ingesting them live. While the data is coming in live through Kafka, we are not doing live ingestion on the platform. We are doing a hourly basis because there is some process to be done. The process includes converting the CGNATs and everything and actually creating an IP data record. And once that is done on the landing zone, then we move them to Iceberg and on a hourly basis. And every hour, once the data is ingested, it is readily available for the LEAs to actually query. So they submit this request from a portal, and that portal kind of converts it into a backend query. And we had to do some optimizations because every query cannot be run. Like, for example, today I have a request for one IMEA for 7 days. I will not run it standalone. It doesn't make sense because there might be 100 other requests for the same 7 days. So I want to optimize how much I'm reading for the number of batches that I'm trying to read. So what we did is we came up with an architecture and a solution for us to ensure we are not reading the same data twice for the same period. So we wait for a certain duration, batch all the requests, and then shoot them in batches where each batch queries 7 days of data in stream. And we have like 15, 20 odd requests running in parallel so that we can serve as many requests as we can for the same amount of scan, so that we don't end up scanning them again and again and again, right? So that is something that we had to come up with based on the use case pattern. So
we might not have time.
Yeah, there are a lot of other optimizations, tools and technologies that we have done, largely around table maintenance. So what it means for the customer is largely they have reduced their overall TCO, right? This was supposed to be a cloud solution. So that is what we could do for them, and largely keep it entirely on premises so they know exactly how much they are going to spend, rather than when it is on cloud, they're dependent on something else. So a lot of other things have been done, some automation, some manual activities, some tools, right? So feel free to reach out if you have any additional queries regarding the use case, etc.
So we do, so me and Ram both can actually talk full day on this topic and this particular use case. But with the respecting the time, one thing I want to leave you with is when you have these scales, right? And especially, so we have implemented a lot of optimization techniques, right? Wherever we can, actually, we tried every single possible thing that we can to optimize this. But I think as Ram also mentioned, that Z-order was the best impact that we could get. So, but the fact also is that not a lot of folks actually understand and see when to use Z-order sorting. So we are here, talk to us on if you want to get more details. But yeah, Z-order sorting is also cool. Think about it, but also think about the use case when you're using it, right? So with that, I'll just the mic to Parth again. So let me
Right. Thank you so much, folks. That was really an awesome talk. Okay, first of all, those who actually stepped outside for having the conversations, really thank you so much. Next up, we have another great speaker, Harini Anand, who is a software developer at IBM's Data and AI division, working on IBM Watson X. She is a published AI researcher and technical speaker who has presented at KubeCon EU, MCP Dev Summit, Google, Microsoft Research, and global conferences. She also holds research roles at UC, Georgia Tech, and Dartmouth, working across ML, systems biology, and interpretable AI. Let's welcome Harini.
Hello. I hope I'm audible at the end. First of all, I think we should just give a huge round of applause to the organizers of the meetup. I've been in a few cities lately, Mumbai and Amsterdam, and the communities are very active. But in Bangalore, seeing a full house it's pretty rare, and I'm really glad that we're here today. So thank you guys for showing up. So my talk is actually inspired by a small side quest that I explore at work. I am a software developer at IBM at the Data and AI division. So What's Next Data is a hybrid lakehouse and the product I work on. And right after my internship, I was sort of exploring what does it really mean to, build the next lakehouse, or what are these features that we see in the catalogs. And one conversation with a senior engineer led to a POC, which is what I'm going to talk about, on how you can, talk to your lakehouse. So just to gauge the audience, I wanted to know how many of y'all have ever used Iceberg in production in the last year? Okay. And how many of y'all have ran an agent at the same time? Okay, so this is the gap that I'm going to try and close in the next 30 minutes. A quick disclaimer, I'm from the infra team of the product that I work on. And if you're interested in hearing more about the different engines and the Spark team or the Iceberg core committer squad, please reach out to some of my wonderful colleagues here who are present, Anshul, Pratham, Soumya, and Tarun. And I'll be talking to you all today about how we really build this next platform, right? And how do we work with open data formats? So one of the things that stayed with me while curating this was the concept of reducing developer friction, right? If you really crystallize what that means, it is to make sure that we're not running manual commands over and over again. That helps us save time, and performance is of paramount importance. So that's where this really plays in, right? So a quick intro. Yeah. Yeah. So I think Parth did a great job introducing. I'm just going to say that the talk is not to position MCP as a shiny framework. It's more to introspect and understand how it can be treated as a systems interface problem, right? The lakehouse is present, and how do we expose it to an AI agent safely without causing any kind of other errors that come in the way of pursuing performance? So let's look at the MCP at a wire level, right? What does that mean? So as you all know, a model context protocol gives us the standard way for any LLM to host or communicate to an agent, right? With external tools, resources, etc. Now, MCP is specifically looking for bidirectional communication, which is why we choose JSON-RPC. So for any kind of local developer workflows that we have, right, HTTP plus an SSE does its job. But for an MCP, we do need this bidirectional implementation. And this is important. You'll see why. So here we see that there's a host that initializes a connection and negotiates capabilities. What are these capabilities? Anything that we want to develop for the Iceberg, right? And for the lakehouse. So each tool here comes with a name, a description, and a JSON. Just to quickly bring back what I was trying to communicate, right? So we're looking at an MCP from a wire level, from a level that is removing all the other abstractions, and we're looking at what specifically are we doing to a lakehouse and how are we reducing the developer friction. So as I was mentioning, we want bidirectional communication, and when we want to do that, we use JSON-RPC 2.0. But if you're doing any kind of local developer workflow, an HTTP plus an SSE does just perfectly fine. So the important part here is the message layer, right? The host here initializes a connection and we negotiate the capabilities. What are the things that we want our MCP server to have? What are the tools we want to expose? So in my use case, I tried and made tools that help list different tables, that help us get the metadata more quickly without me manually entering 100 SQL commands to get the same. So we expose this as a JSON schema, and when the model decides that needs a specific tool, it will do the specific call, right? Like we have tools call. If it wants a specific data object, we use the resource read. And if we have noticed that, hey, we're doing this constant process again and again, we can put that together as a prompt template and save that under the prompts, right? So the key primitive here that I'm trying to talk about is tools. We're going to expose the Iceberg catalog capability as specific tools. Instead of the model knowing exactly how to call the Iceberg REST API, we're going to have these tools, and you'll see how this actually helps, right? What are the benefits of it? So let's quickly map the REST endpoints to an MCP tool, right? We have the catalog that already gives us a stable API surface, nothing new. For example, we have get namespace, and that naturally lists all the namespace. If we want specific tables, we have list tables with namespace as a parameter. The heavier endpoint here, if you notice, is the metadata, right? When we want to return the entire Iceberg specs, the snapshots, the definitions, things slowly start becoming heavier. And this is what we expose as a tool called describe table. For any kind of snapshot specific access, we have a tool called get snapshots. But here's where we need to be a little careful. Why? Because a single snapshot metadata can include even the manifest. So that will automatically increase the pagination process. Authentication is also very important. We have auth tokens that should not be a tool. Why? Because we do not want to expose any of these tokens in the tools. The token retrieval should be specifically present inside the MCP server, right? Inside the client, the HTTP client. So any kind of dangerous operations, if there are folks here who've accidentally deleted things or have to write something that you perhaps don't have access to, we need to counter into the fact of those things as well, right? They need a different treatment. We need confirmation gates, we need any kind of human in the loop approval, etc. So the mapping here is pretty straightforward. We see that there's an engineering discipline that helps you understand what do you want to expose and what is it around. If you look at the full system architecture, there are basically 3 primary runtime boundaries, right? On the left, we have any LLM host of your choice. Some of us have our internal LLM, some of us like to use open source, whatever that is. This is where the user comes in, and the user can be a developer, it can be an SRE, it can be a customer. And here is where they come in, and the LLM helps perform inference. It decides which tools we want to expose, where do we want to inject the result, and how do we generate a natural language. The middle layer is what we have as the MCP server, where we bring in our engineering decisions. So this is kind of a parallel to a control plane, right? We have tool lists, you have calls that helps trim the responses, have different injection tokens, and normalize all the errors. And finally, on the right, we have the catalog implementation. So this doesn't have to be specific to just one thing. It can be extended and experimented with different things like Polaris or even the Unity catalog, Hive-backed any kind of catalog that you might have, or anything that exposes the Iceberg REST API endpoints, right? So the main 2 translation protocols that's happening here is, first, the LLM talks to the MCP, okay, which is completely JSON-RPC. And the second is the MCP server talks to the catalog. So these 2 are happening independently and happening in sequential fashion. The key idea that I'm trying to drive home here is that the LLM doesn't need to specifically know the catalog internals. It only needs to know the tool layer, which is what we bring in the middle with the MCP server. That becomes the boundary which helps us enforce trust, right? And the response size, the amount of errors that come up automatically fall into the safety policy that we try to build. So this is why I think it's, MCP is less of an agent magic tool that is brought upon, but more of a safety protocol boundary. If you look at some numbers, I think I would call this to be one of the important slides, because you can clearly see how raw Iceberg metadata can get very large very quickly. Now, the issue with that is a table metadata response, as you might have seen, can have hundreds of data in kilobytes. And if you dump that directly to an LLM, just like if you query anything to an LLM without context, you blow up all the important information, right? You increase the latency, you increase the costs, and you confuse the model. So it's really helping nobody. So we need something here to prevent that from happening, which is a response trimmer. So here you see an example where we have a raw input of around, say, 500 KB. We stripe the manifests and the statistic references, right? So that alone brings down the amount of data that we put in significantly. So what are we finally keeping? We're keeping only the current schema, and we're dropping all the historical versions of other data that's not explicitly requested. Finally, we paginate these snapshots. So here we have it for the latest 5. You can change that number according to your use case. And finally, if the table is pretty wide, we can trim that, right? We summarize the columns and trim the keys. So the final target payload is under 4 KB. The design principle that you can take home here is very important, right? Each trimming pass cannot be done half-assedly. What you should be doing is make it unit testable. What I mean by that is you should be able to test that so that the manifest parts are striped and you're able to see that independently. So it's not an optimization that you add later in order to improve performance. It starts from the ground, from the first principles approach. So if you have to look exactly at what do we keep and what do we stripe from a sample table metadata, this is what that would look like. We have a lot of information, right? We have the format version, the table ID, the location, the schemas, the partition specs, all of the snapshot logs, the metadata for those snapshots, etc. If all of this goes into an LLM context, as I mentioned, you start getting hallucinations, and that's where performance goes down. But for a normal describe table call, all of this is absolutely not necessary, right? The model needs only the identifier and the current schema ID, and maybe some 5 recent snapshots. So what we are doing is we're not putting the entire manifest list into the LLM, right? We're using Puffin statistics and every historical schema version. So this is where the engineering design plays a pivotal role. If you're bringing in an external thing that brings safety, we also have to make sure that it prevents us from increasing costs, prevents us from using additional resources. So that's how you balance the trade-off, right? The model here now receives enough information to answer any user's question, but not so much that it starts reasoning over irrelevant internals. Another major point I'd like to highlight is the tool description. So we have a weak tool description like get table, and you can clearly see get table info is not enough. Why? Because the model does not know when to call it. It does not know when not to call it, whether it's expensive, whether it's returning the schema, whether it's doing any of the things that actually needed, right? And that is what causes bad agent behavior. It's not the model spec, but how we use the model. So what do we do instead? To prevent hallucinations, we have a better description. So we see that describe table returns table metadata for one table, including a current schema. So what this is doing is it is using it when asked about a specific structure. It will not call it for every table. It will call only list tables first. That is the first tool call that's being called. And then it basically gives an agent operational constraints. So my rule of thumb when I implement things like this is that every tool description, specifically with MCP, must come with 3 things. When should it be run? What does it return? And when should it not be run, right? This often automatically improves the agent behavior by a lot instead of switching models. So this is kind of the money diagram. I think it shows the agent, what goes wrong and with weak descriptions, and also what's the correct one. So I do have a demo that might help understand this better, and I've shared the link for it as well. But here is an anti-pattern, right? On the left, you see the user asking, tell me about sales tables. Because the tool description is weak, the agent calls describe table for every possible table. Orders, customers, products, lists, and maybe even a hallucinated namespace like warehouse. Now we have multiple expensive calls. When you scale it to production, all of this becomes 100x, right? So the total time around for this is hundreds of KB of context. But on the right, you see the correct sequence. The agent first calls list namespace, then sees that it has list tables where we're specifically looking for sales, gets the available tables, and then describes them. For example, in my case, orders. So the pattern we want here is cheap discovery first and then expensive description. So this is not just only about latency, it's even about controlling the agent behavior through tool design primarily. So what breaks before production, right? The part that I think scares a lot of us, it does scare me a little. The first issue is catalog auth delegation. So in a real deployment, you might have a different auth client to get a specific token from this tool. Now that token, as we know, because we rotate secrets, we rotate tokens, it will expire, right? So that is why we need to make sure that it's refreshed server side, ideally before expiry. The token should never be passed into any kind of tool, and the MCP server injects that auth into the HTTP client. The second thing is the context window budget. Coming from a cost perspective, the metadata can be from 50 to 500 KB, even more if you're using for a larger use case. And you need a target, like 4 to 5 KB is what we usually work with, right? That is more than enough to summarize any kind of white tables, to paginate snapshots, to stripe manifests, etc. The third is the discovery versus the description, right? This is a kind of an interesting trade-off where you can spend some time understanding, for example, here, right? We have list tables that's very fast and very cheap, but describe table as a tool is much more expensive and heavier. So you do not want the model making n expensive calls when one cheap discovery call does the job. That is where you choose the trade-off between description and the discovery. The fourth is the read safe, right? Security is always paramount. So how do you have structured confirmation and human approval being looped into this setup? A good pattern is having a specific tool called confirm action, where the server returns any kind of action plan and executes it only after the user has explicitly approved it. So these are the 4 areas I would not postpone. They kind of determine where this becomes a POC and where it can be taken to production grade. This is a decision tree that I think can help make better decisions on when do we have sequence tools. So if we have a user that says, what tables do we have, right? That is discovery. Agent calls the respective list tables, but only after it has called list namespaces. So the sequence here automatically saves us time, context, cost, and a lot of unnecessary tool calls, right? If the user is asking specifically with the keyword describe, then we automatically do the describe table. If the user is asking something with time travel or something which has to do with sequence and there's what changed in the prompt, right? We have the snapshots. We describe the table if it needs specific schema context. So the final answer that is synthesized by any LLM or agent that you have on the other end comes from facts that are built from specific explicit tool results and not from a fetch that you cannot trace back on its authenticity. So that distinction matters, right? It is the reasoning that lives over the metadata. So this is a checklist that I would this is a checklist that I would have before calling it, production grade ready. One is that auth must live in the server. The second is every tool response should pass through a trimmer at a dispatch layer. Do not rely on individual tools. Make it, central. And third is all these should be enforced within the tool description. So when we have something that is only read-only, the get endpoints get exposed first. Fifth is that errors should be structured. I think if you don't leak any stake traces to the model, it automatically saves us a lot of time. And the last but not the least is log tool calls at dispatch. This is what helps you debug any kind of agent behavior. So in my POC, I used Grok for its high inference and low latency. If you choose to use Langsmith, any of those other things, I think even Helicon, in fact, whatever observability stack you use, all of these come in handy and it's cross-implementable. So the theme is MCP server is not just a bridge, it's a policy enforcement. So I still want to give an honest assessment of what works and what doesn't. And the fun part of what doesn't work is that it opens up new places for us to solve problems, for us to find ideas. So what doesn't work that you can see here is the partition value enumeration. It's still very expensive, and you may need a separate tool for that. If you're working with multi-table joins at scale, then it's hard to have the context being filled up before the model has even planned this query. So LLMs can hallucinate even after a partition filter is applied, that no doubt, but it only happens when you don't ground them with actual data. So if you can be more specific and prescriptive with what tool calls you're making, you can automatically avoid these. So the honest answer here is that MCP makes the interface much cleaner, much more faster, but it does not eliminate some data system problems that are still present. So this is the demo, but I think in the interest of time, you can check out the repository, and I was going to show it, but I'll walk you through what it basically has. So we have 3 basic files. You can build it in Python or Golang. Golang is 100x faster, but it might not be integratable with your current code base if it's in Java. If not, Python is pretty fast. FastMCP is the tool that you can use. We have a mock, catalog, which is being exposed via a REST endpoint. And then we have a server where all the tools are registered. You define and engineer what are the tool calls you want, and that comes under the MCP Python SDK. And finally, you have a user-facing interface. You can use Claude for it. You can use your own client surface. That doesn't matter. So what that does is it calls the Grok API and loops it till the final answer. So yeah, I think the main summary that I want to share is that an Iceberg REST catalog can give us a stable public API interface. Building an MCP server on top of that is not really a massive engineering problem, as you just saw. A basic version just does the perfect amount of work needed. And second is the fact that tool description determines the quality of the agent behavior. A precise tool description prevents hallucinations. And third, with the amount of data we work at scale, response streaming is very important. So if you are building the trimmer before you test it, it helps you make your tables much more faster. The fifth one is, you start read only. So any kind of write operations that you might have, hold it to the next part, right? Unless there's an explicit RHLF in the loop or a human in the loop. And finally, you'll notice that an intuition that builds upon this is this pattern kind of generalizes. What I mean by that is if you look at Iceberg today, it works, right? But if you extend this to maybe other lake houses or other catalogs like Delta Lake or with Hoodie, you might have other metadata services that can also benefit from this. So the bigger idea that you can see is that the future of any kind of data agent is not just dumping more schema. It is actually giving models safe, live access to the systems that they need to reason over. So I hope this inspired you to go chat with your senior engineers about the ways you can improve your product, to learn about it yourself, or even experiment with things like MCP and other things that might help make things better. I'd love to take questions if you have anything specifically over the Iceberg metadata, or what would this look like in a production environment? Because I'd be happy to chat. Or if you have any other questions, feel free to find me here. Yeah, thank you.
Yeah. Let me open up the platform for questions. I have already one in queue, so I'll just hand over the mic.
So first of all, great presentation. Thank you so much. So you talked about tools, right? So I wanted to know your perspective on prompts also, right? So if we talk about MCP, tools, resources, and prompts are the key. So when we talk about Iceberg, what kind of prompts do you think generally, or best practices do you think from prompts perspective should we look for?
Great question. So I think one of the primary instructions that I followed was we often, include what we want the prompt to do. We don't include what we don't want the prompt to do. And in that process, we get a lot of data that, or, responses that make no sense or are additionally irrelevant. So what I do as a best practice is I first, mention what is the exact objective of this tool call. And I mention what I specifically don't want it to return. And that automatically improves the quality of response I get and saves a lot of tokens.
So and with prompts, there is another thing that we need to define about the model, right? What kind of model you use behind the scenes. So what kind of evals and guardrails do you think generally we should think about when we talk about different models?
So I had worked with Llama. So with Llama, you have 3.3 billion parameters being in the play. The main evals that I made sure was making it not hallucinate at a point where I'm not using all of those tokens, right? It's important to downsize according to your use case. So when you're first starting out, trying to experiment and see what specific tool calls you want to make and what is the data that you're fetching and what automation is really being made to remove the developer friction, you bring in that hallucination fact check, right? So that definitely helped. And other than that, I think the standard benchmarks that are present for evals with Langfuse, those do just fine.
Awesome. Thank you so much.
Thank you.
Harini.
Yes.
Heads off to you. You are brave enough to deal with Llama. And let's talk more, because I have a similar solution working in production. My question to you is that your thoughts about how do we deal with the semantic context, because the schema description is not enough. The devil is in those particular details, like any complex queries and all. You need to know what those tables may contain more than what their schema looks like.
That's actually a great question. In a parallel project at my work, I worked on basically something similar where we wanted to bring in the semantic context. Just giving the syntactic context was not sufficient, right? So the way we saw the most success with semantics was building in personas. So we built 4 specific personas like sales, technical, etc. Because with that, you were able to feed in additional context that you didn't have to pass in at every single call while building this. So those personas were sort of like plug and play. We could choose that persona. For example, if I'm looking at a business use case and trying to see where does this stand from a competitive edge point, then I took in that persona, and that automatically had all the metadata, which brings in the semantics. But if I'm looking at a technical spec point of view, then the tech persona helped. So I think defining clear personas automatically bring in the semantics. And yeah, I think it's a pretty interesting concept. I'd love to chat more. Thank you.
All right, I'll get 2 more questions and then we'll push the remaining questions in the networking section. I've got one over here.
Hi, I'm Karan from Cisco. And when you were talking about it, we saw that there's a lot of post-processing you're doing after you get the Iceberg metadata response. So are you using an LLM within your MCP tool itself to summarize? That is one question. And the second question is, because there's a lot of post-processing involved, I saw you have, WebSockets and HTTP and SSC. Did you consider Docker? Because it's very compute heavy. So might as well the user may compute at their layer. So are you using LLM within your MCP tool itself?
Right. I think that's a very interesting question. So for the first one, no, there's no LLM inside the MCP. So the flow is we have the catalog, and after the server, right, on the client side is where we have the LLM. So the main developer friction point that I was trying to talk about, or what I tried to build here, was removing the friction of entering these commands or trying to fetch the data. That is the friction. Now, does that summarize and give me the succinct answer at that go? No, that was not the problem, right? So we optimized for removing the manual commands. The LLM here is specifically to interact with the server and the catalog. And
okay,
the
so the LLM who is calling your MCP will summarize on your behalf after the previous tool calls have happened.
Yeah, so we have an MCP server and a client, right? So the client is where I have the LLM. There is no LLM present in the server to sort of change or optimize the queries that are being fetched from the Iceberg catalog.
And you are only doing Iceberg catalog and metadata, and you're not doing on the real big data, right?
No, so the real one that I had experimented with Presto, where we basically have different engines in our lakehouse for what's the next data, and the goal was to see which of these components or pieces of the puzzle can be interacted through this MCP server. So with Presto I did do the real one. Here for a mock simulation I used the Iceberg catalog. And the second question for Docker, that is actually one of the containerization techniques that we use, right? That is a very standard way of going about things. Some of the enterprises are not compliant with Docker. They have their internal things. So that is where I think you choose the engineering decision of which one do you pick, and what are you optimizing.
Folks, any more questions?
You were telling we need to productize in terms of user personas, and that makes it better, right? Can it be completely productized, or you need a forward deployed engineer pre-post using of the product? And what is the percentage of forward deployment engineers required and product builders required? At least your team and few friends' team. Can you give an estimate?
Right. So a forward deployment engineer is a completely different role. I understand where you might have thought of that fitting in here. I think that comes in with the complete product and between the customer, right? They act like a bridge between the two, and they also have the technical capability of adding in more enhancements to the product. The personas here actually help, let's say, a user or a customer themselves interact with the product. So in addition to this, if there's a next level of interaction needed or further communication, that's when I think a forward deployment engineer would come in. This would be pretty basic for them to be a part of. If it needs an advanced level of interference, then that's where they would be present.
Can an advanced level of personalization, can it be productized?
Yeah, I think that is completely dependent on the person who's designing these personas. So if the team does come up with a strict, has the end-to-end details of that, then that automatically could also be a persona. Yes.
But you have not tried it out.
Yeah, that is the right thinking process.
Yeah, thanks.
All right, folks, if I can request the rest of the questionnaires to be waiting until the networking section, that will be helping me to drive the event forward. All right, thank you so much, Harini.
Thank you.
Yeah. Good number of questions directly translates to a well-received talk. All right. Now let me tease you all a bit. I'm not sure about the entire audience, but I at least can smell the aroma of the good food. And it's really very tempting. I'm not sure if I myself can hold on to another hour. That is what we have left. We have 2 talks and then couple of small plugins of about 2 to 3 minutes. And that is when hum sab toot padenge food pe. All right. So yes, with that, we have the next speaker, Shreyansh Roy. He's coming from Amex, American Express, who is a software engineer 3 at American Express, where he's part of the enterprise architecture team, working on scalable distributed systems and enterprise grade architecture. An active community speaker, he has presented at platform engineering AI meetups and technical conferences across Bangalore on topics spanning autonomous pipelines, AI engineering, and system design. With that, please, let's welcome Shreyansh.
Good afternoon. So what is the Iceberg maintenance problem that everyone talks about? And why do queries actually degrade and Iceberg tables actually degrade in time? Yeah. So consider a newly ingested Iceberg table. On day 1, the table is perfectly fine. Queries are fast, metadata is small, and storage is very optimized. Fast forward to next 6 months, this table has been receiving continuous CDC updates, streaming inserts, deletes, schema evolution happening, and thousands of commits are happening on the table. So after 6 months, this is how the table looks like. Now, the queries start becoming slow, the planning time increases, the cloud costs hike, and the Spark jobs take a little longer. So what happened? The data did not increase drastically, but the table structure definitely did. The reason? An Iceberg table is not just a data file. Instead, it consists of delete files, manifest files, metadata files, manifest list, snapshots. The reason being, every write on an Iceberg table creates metadata. Every update operation creates deletes, and every commit creates snapshots. This is the reason why, along with the data file, we have multiple files as well when it comes to an Iceberg table. Now let's see what are the different factors that actually contribute for degradation of Iceberg tables over time. The first and the most popular problem is the small files problem. Now imagine the Iceberg table receiving continuous CDC updates every minute. So now every ingestion that happens creates Parquet files. Instead of 10 Parquet files of 512 MB, we have 100,000 Parquet files of 50 KBs. These are the small files that we talk about. And the query engine, now when queries the Iceberg table, has to actually read all these small files. So eventually, the query performance goes down. The second factor that contributes to the degradation is the delete file accumulation. Now, Iceberg supports row-level deletes. So when a delete operation happens on an Iceberg table, it does not rewrite the entire data file. Instead, it records that in a separate delete file. So eventually, in the course of time, when the table receives multiple deletes, every data file in Iceberg is linked with multiple delete files. So now when the query engine tries to query the table, it cannot just read the data file. Instead, it has to also read these delete files, which is associated with the data files. This is the delete file accumulation problem that we talk about. The third problem is the slow query performance. Now, the table grows with time. So does the snapshot, so does the metadata, and so does the manifest. And eventually, now the query takes longer time to plan before it actually starts to read the data. Next. Yeah. So why is this delete file a problem? Iceberg supports 2 basic types of delete approaches. The one is positional delete files. Here, the position of the delete and the path of the file is contained in the delete entry. So now when the query engine tries to read this delete file, it will locate based on the position. Whereas on the equality delete files, we just store the values. So now whenever the query engine is reading a table, it locates the delete files with the help of this value. Coming to what does COW and MOR mean? Now, for example, we have a big Parquet file containing 1 million customer records. Now, I just want to change one row, one customer's address. So what do? There are two approaches to this. One is either I rewrite the entire file, or second, I just record the small change in a separate file. These are the two approaches which are called as copy on write and merge on read. Now, if I rewrite the entire data file to accommodate the one small row change, that is expensive while writing. But when it comes to read, it is very efficient because the query engines now will just read through the data file and does not have to look through the delete file. Whereas if I just record that one change in a separate delete file, when the query engines will try to query the data, it will have to merge the data file and the delete file, look for which rows got deleted before actually displaying the result. So MOR is very write efficient, but when it comes to read, it becomes slower. Yeah. So why do queries actually take time? This is the question that everyone asks. The reason why MOR table queries take time is because every data file will now have so many delete files connected to it. So now when the query is executed, it will read the data file, it will read the delete file, it will compare the rows to find out which rows have been deleted, and it should ignore while giving the final result output to the user. This is the reason why users often complain, saying that queries eventually become very slow. This is where maintenance operations come into picture. Iceberg maintenance is a solved problem. Many existing solutions give maintenance solutions. Users can use Spark scripts, ad hoc scripts, and some vendor lock-in tools also provide managed Iceberg maintenance solutions. But doing maintenance is very simple, but knowing which table to maintain at what time is the real challenge that we all face. Now imagine a team has scheduled maintenance in midnight, but do all tables need maintenance at that particular time? The answer is no. Some tables might need maintenance, some might not need them at all, and some might need it very frequently because of the frequent CDC traffic that happens. Hence, when we schedule maintenance on one fixed schedule is not the solution to the problem. Actually, maintenance should be driven by the health of the table. It's the health of the table which actually indicates whether the table needs maintenance or not, right? Next. The existing solutions which are available are Vanilla, Spark. Existing solutions have their own pros and cons, like Spark is open source. It can be configured very easily. It gives a good amount of optimization, not denying the fact. But almost every time the entire file is rewritten, which is an expensive operation and also time consuming. Also, there are too many configurations to be configured, which becomes a hassle because when you have to schedule compaction on so many tables, the overhead increases. Coming to S3 tables, S3 tables is a managed solution which is available. It provides automatic compaction and cleanup. It works well with Iceberg compatible engines. However, it is not open source. It gives very less flexibility to the user to actually tune it. And it also gives very limited or almost no amount of observability so that user can actually see that what happened after maintenance and before maintenance. So the problem here is we need maintenance, but we should also get an idea that after the maintenance operation is performed on a table, did it actually work? Is my query now better than how it was previously? So what's the solution? I'll now hand over the stage to Ankit, who will walk you through the solution that we have designed, where we have overcome these traditional limitations of the existing solutions.
Hey, hi everyone. I guess I'm audible to everyone, right? So no one wants breezes like Easypura, right? Which never goes to production. It's taking a lot of time, right? But the same case here in the Iceberg tables as well. No one wants tables to be very cluttered, not queryable, not production ready. So for this, and we also discussed the open source solutions that's available in the market, and also the solution that's closed source, but not fully configurable according to user requirement. So we've come up with a solution, which is OLEG Fusion. Yeah, so OLEG Fusion is an open source tool, fully configurable, where you can configure your jobs according to a table and run the compaction accordingly, where you can also clean up your files, which are like orphan files are there. So you can clean up that as well by configuring the cron. So if I little dive on the architecture of the Fusion, it's actually using Spark to orchestrate the workloads. So what actually happening is, first of all, whenever Fusion runs, so it divides the task in such a way that no shuffling will happen inside the executors. So if shuffling is not happening inside the executor, that means it will be having the less memory consumption as well as a faster performance. So that's how Fusion is dividing the task. And also you can configure how many tasks need to be run in parallel. So let's say you don't want to run a lot of tasks, maybe you have some resource limits, so you can configure that as well. So every capability that you are getting in vanilla Spark and the capabilities that you are not getting in the closed source tool, that you are getting in the Fusion itself. So just a walkthrough how Fusion works. So as previously in the Razer Pay talk, people mentioned that they have use case of the absurd scenarios. They mentioned that how they come to the 5 minutes, but here we are saying you don't need full compaction every time. That's why we have 3-tier design, in which we are saying that, first of all, what is making your query slow? The equality deletes. And why you need equality deletes? Because you want write to be fast, right? So if you don't need equality deletes to be queried, you have to convert it to the positional delete. So that's where the first type of the Fusion compaction comes, which is light compaction, in which we are just converting equalities to the positional, which is very fast to read. Not to write, but for the read. And we are writing equality by the ingestion tool, but you can ingest via any tool you want. Then there comes this light compaction also merges this small files. Let's say whenever you're ingesting, you are not ingesting, let's say 1 GB of data at a point of time. Your CDC workflows ingest, let's say 30 MB, 40 MB small files, right? So those small files can be merged by the light compaction itself. And we have seen it on the TPCS table itself, that it's take 2 to 3 minutes just to run this compaction, and your queries are as good as the your vanilla Spark compaction that you are going to run. I guess Razer Pay people already talked about Spark vanilla compaction. So then the medium compaction comes into the picture. Now you have to apply those positional deletes as well. Like in the V3 spec, we have DV, right? So positional delete can be multiple for a particular data file. But in the DV, there is no positional, like in DV are the single one for the one single data file, right? So here in V2, we have multiple positional delete for one single data file that need to be merged and that need to be applied. So that comes the medium compaction into the picture, which applies your positional delete files. It also converts. And then it also merges the medium files, which is here, which are greater than the 8th part of your target file size. So let's say if I have target file size of 512 MB, what will happen is the small files, which are lesser than the 64 MB, the 8th part of it, are these files. These getting merged to the bigger files, which is then converted to medium files. Those medium files will be merged by the medium compaction. So now comes to the third full compaction, which is again similar to the Spark compaction, but little faster due to our strategy that I will mention at the end of the slide. So these are the 3 compaction which you need, which you don't need the full compaction every time. That's what our theory is. And that's where the Fusion comes into the picture. Now comes to the Fusion. What's the feature Fusion is offering? So first of all, the configuration, table level configuration you can do. You can have the health score. Health score is depending on the small file sizes you have. Also, this health score will tell you whether to run this compaction or not for this table. Then comes the table metrics. How many files, data files, delete file, positional date, equality date you have. All these are also available in that. Like the observability for the whole Iceberg table is available inside the Fusion, which you can like generally decide if you need the compaction, if you need the read optimization or not. So one more thing here, there is a problem of conflict, right? And we can't avoid with respect to the positional read. So here comes how Fusion is doing it. So whenever you are running an ingestion, Fusion takes care of the positional date in such a way that if it is a granular file granularity or partition granularity, let's say it is a fine granularity and that file is added right now, Fusion just take it as a new ingestion. It doesn't conflict with that. So that's how it avoids the compaction, but some kind of positional dates, let's say it has granularity of partition. That means it's affecting some files which already compacted, right? So in that case, the conflict still come, and we are looking on the solutions, like figuring out the solution how we can come up with this. But currently, it's fully conflict free with the equality reads and the positional reads which are adding the new files. So how equality to positional conversion work? So as I mentioned, we are a little faster in this as well. So in the Spark, what happens is it's read the full table in the memory, which is not required for the positional conversion. Only one column can be read, and also from which file it is being read, we can just directly detect it and write the positional directly. So that's how the less memory is being used. The optimization logic itself is doing that. How the full compaction is faster than the Spark, vanilla Spark 1. So in the vanilla Spark, you can see that file 1, file 2 is being merged first in the single file. Then this process happens sequentially for all, right? So this is also a time-taking process. But in Fusion, what is happening is, first of all the files are being parallelly processed, merged in the light compaction to the medium file size. Then the medium files are being merged and converting it to the full file size. So coming to the benchmarks, like as I mentioned, these two strategies that we have implemented, that we already have, is taking very less time. What we have done is we have run the benchmarks with respect to TPCS table, the TPCS, and like how it is apple to apple, just explaining you. So we ran a query, TPCS 6 query, which is running for 2 hours continuously on 2 tables. Both our tables are compacted by vanilla Spark and the Fusion, where we are running full compaction here, and here we are running tearing compaction. So we got the same query performance, but in the less time. So less time means resource consumption is less. That means 50% it's cheaper. And again, it's 2x faster than, So it's again 2x faster. So this is how comes the benchmarks. Now, anyone, if you have any questions, just you can ask.
That was a lot of energy. Thank you so much. Much needed energy. Questions, folks? Thank you.
I have more of a basic question. Like you mentioned in one place, that you're not reading the entire table to get the position to the file mapping. So but how will we get that without reading the entire table? Like we need to.
So what happens is we read whole equalities first, and we streams the files. We only read the column of the ID, which is identifier column. That identifier column is being checked in the equalities. If it is present, we know from this file we read, we are streaming it, right? So we know which file is being read and which position it has. So we just write the position for this, but we are not loading the whole file.
Got it. So during the streaming itself, you are identifying that.
Yes, but equalities are there in the memory.
Okay.
So if you are doing 100, 200K records will be there, right? And 100, 200K records, since IDs will be there in the memory.
Got it. Thank you.
Any more questions?
Term mode beyond connectors. And one more is that, how are you ensuring that, the system doesn't collapse when, your downstream tasks slow down and your upstream keeps pushing it? So how are you managing that part?
So, sorry, can you again ask?
Okay, first answer the first question in terms of your mode beyond connectors.
So our moat is to adopt to help the companies to adopt the Apache Iceberg table format in the very easiest way possible. Like right now, if you see, people are not generally generally don't know about the open table formats. They can vendor lock out. They have the interoperable solution. So we are making sure that it will be easy for them. So back pressure collapse, we have a feature which is watermarking, which is in the staging phase, which is going to make sure that all the reads, all the wall logs that's there in the Postgres being read in sequential manner with respect to the full load as well. So, and also, sorry. So more technical depth I can say is so what will happen is there will be two tables. Okay, so one is main table, one is change log table. Main table is being already full load will happen in that, and the CDC will happen with respect to that only. And OLEG itself is so much faster that it's around almost 55K records per second it's processing in just for the those wall logs. If you have more than that use case, then we might have to do some sort of chunking in that as well. But in the sequential chunk, it might not be like sequence mode will be there. Like we need wall logs to be sequential inside the lake house, right?
All right, we have got last two questions queued up.
Hey, it was really nice presentations. So I just have one question related to deletion. So let's say let's say we do multiple updates on the same column, same rows. So let's say row 1 is updated 4 times. So do we have 4 rows in the deletion files, or just a single one? Do you compact and write the single entries?
In deletion file.
So if
in deletion file, it will be only single row.
So even if I update 4 times to the one row, it will compact and just add a single entry over there.
Yes.
And about compaction, so what I understood that basically you are doing hierarchical compaction. So just like I think CLIDB does, like first merge two small files and then bring a one tier, then merge smaller files to one tier. So does Spark not provide any config to change the compaction strategy?
So you need to write your own optimizer for that.
There is no out of the box
So all
solutions.
vanilla Spark logic is there. That's doing the same thing that I presented.
Okay. Thank you.
All right. One last question before we move on to the last talk of the day.
Thanks, Ankit, for the talk. So few questions around, have you ever encountered concurrency issues like version conflicts while compaction commits the file and while CDC ingest is subsetting to the table?
So currently we have tested with the OLEG Go, which is an ingestion tool. OLEG Go write equality and position only for the new files that's being added with the file granularity. So whenever we are ingesting it, so first compaction will happen for the whole snapshot. From that snapshot, whatever files are being added, all these are picked up and pushed with respect to that compacted snapshot. So in that way, OLEG Go doesn't face any conflict. But let's say if you are running with respect to Spark, as I mentioned, some kind of positional date will not be spotted. So let's say some files got deleted, which inside the compaction got deleted, but you are writing a positional date for it. It will be a conflict. So those kind of conflict handling, we are still in the process, like how we can solve it.
So, okay, you are in process. And how about streaming solutions? Like, do you also offer like compaction while a streaming is ingesting the similar records into? So in that scenario, there will be the frequency of version changes would be way higher than a batch.
Yes. In the streaming way, as I mentioned, once the compaction is done, whatever ingestion has happened after that, we just pick up the whole files. That whole files are committed with that.
So will there be file size differences as well, right? So you are doing on a tiering basis, right? Some are small files, then you're increasing to a bigger chunks. So probably like the newer files, where are you actually adding those files into which size basically?
Which size, sorry?
So basically there would be, let's say 5 MB inputs have come in the last 10 minutes for the ingestion. So then again, you are running the compaction job.
So next tier of compaction will pick it up. Not this one. This one only compacted the previous snapshot. That's where the compaction started. So next snapshot will take care of the ingested file which have the less size.
Thank you.
Thank you. All right. Absolutely last talk, promise. But we have 2 more plugins after that. Each of them will be about 120 seconds long. Yeah, we have Shreyansh and his system is fixed. So yes, over to you.
Thank you. So am I audible at the back? Back people can listen me? Yeah, so already 2 time introduction happened. So because of the presentation issue and all, and I'm the last speaker, I know that I'm the one who is delaying your lunch and all. We all are hungry. So I'm trying to wrap it faster. So like as I listen to all the talk and also more like as this is Iceberg related thing. So more talk is related to data engineering thing, but my talk is mix of the data engineering and full stack domain talk. So like as you see from the topic only that from Express API to LLM. So I will give little touch on the Express, like which is the backend framework for JavaScript, like Express.js, and the LLM now a hot topic everywhere it is there. So even though we are a full stack developer, we do have to work on the LLM and all, like some chat application is there. And as a full stack developer also, we have to work on that. And when we are dealing with that huge amount of data, so our talk is that even with the help of full stack and all, how you will going to deal with like now like this high intensity data, especially in the petabyte level or things like that, where we will going to train any Gen AI model and all. So the thing is that so as a full stack developer or even a data engineer, if you will go with any traditional database, like any kind of database, whether it is PSQL, whether it is MongoDB, like object-oriented database or Cassandra or whatever the thing is there. So we know that like especially when we have to deal with lot more of data, then we have some bottleneck of throughput, like read write output, read write cycle have some issue. So like that's why we are doing like a bunch update and bunch read kind of thing is doing, like especially any kind of application that we see Uber and all. So like they are doing bunch batch update, and for read kind of thing there are different kind of database that we are citing in different level and things like that. We do have lot of replication. So especially when we have to deal with the like the petabyte level of data and all, then we cannot do that much replication because the cost factor is that much higher. So we will not able to perform that well, and we will not able to provide the solution to the end user in a much optimized cost manner. So that's what the thing that the scaling wall is, especially the traditional database fell at petabyte level historical data, because we know like there is a talk also on Gen AI and all. So we do have lots of data, and also like it will not going to hallucinate, and also we do have to train with multiple data, and also most historical data that someone will ask something, so it will going to have like RAG will going to work, it will going to give some similarity score, and depending on that it will going to give the output and all. So like the traditional database fails here. And day by day, as we see that right now the 70%, I saw somewhere in this slide that annual growth is 70% on SaaS app, log and event. So usually like from the log and event, we are getting every year 70% more and more data. So like for dealing with that huge amount of data, it is a very big issue. If we will go with the traditional database or any kind of serverless also, then the cost will be very much higher. So this is the thing. So that I'm talking to that SQL and NoSQL limit, like especially for the like high traffic, there is a limit. There's a cost is a very big factor that we have to deal with. So that now the thing is that the big data requirement came into the picture. So big data requirement came into the picture. So especially when we do have the click stream and all, like we all know that Amazon and all, whatever the click we are doing and all, they are storing that click also, that you have click on any basket or something of that sort. So click stream data and all. And so when we do have that huge amount of data, so it is very hard for us to store in any kind of traditional database. And we will going to migrate to any cheap kind of storage. Like right now S3 is there, GC like Google storage is there, and things like that. S3 we all know that it is AWS S3 bucket, like cold storage kind of thing and all. So we will dump the huge amount of data there, and that is our big data requirement. And finally, for the Gen AI and RAG pipeline also, we need a high level of data, and we need some kind of tool which have the ACID compliance also, that if we will going to change something with the data, or if you will going to change something with the with our whole pipeline, it will going to trigger that, and it will going to update in the cold storage also, whether it is S3, whether it is GCP or somewhere which is very, very cheap and all. So now for this, all the problem that we are facing now came to the part, like this Apache Iceberg is one tool which is helping us to deal with all these things. So yeah, usually the Apache Iceberg is the tool which, like any cold storage also, we will like cheap storage like S3 and all, where we will going to store lots of data in very like 30% or 40% less cost, or maybe even 70% less cost and all. So then it will going to have cold storage, and depending on their feature of the Apache Iceberg that most of the speakers said, that it have the metadata information about the data, it have many other capability like acid compliance is there, like time travel feature is there, and snapshot related feature is there, so that even in history we will going to grab the information even from the cheap storage. So we will dump, rather than any traditional RAM and all, a database RAM, we will going to dump it in a cheap storage with the help of the Apache Iceberg, and Apache Iceberg will going to trigger with the help of their metadata, and it will going to give real-time output from that high level petabytes of data, where it is very harder for any traditional database to come with. So so this is the table format that especially the Apache Iceberg is storing the data, and with the help of this table format, it is called perquet file and all. So with the help of they have all the feature like a snapshot feature, time travel feature, schema evaluation, that is acid compliance. So whatever the thing, it will not going to break in between and all. So it have all the acid related atomicity property like that we heard, like database, traditional database have the acid property, and also it do have all the property. So this is the graph, like data is getting higher, and cost is getting lower, especially with the kind of Apache Iceberg kind of data lake houses. So now coming to our pipeline, that is my topic, that from how as a full stack developer from Express API, you will go and you will have it Gen AI ready LLM system and things like that. So finally, the thing is that we will going to have one Express servers like backend server. We do have one chat application, or like some chat application is up and running. So we will have backend written in Express.js with the help of JavaScript and all. And we will have here Kafka, because the thing is that we will going to store all the data which will have while training from the Kafka, so that multiple publisher subscriber is there. So that even though some subscriber like Kafka, like Apache topic or some other topic also in the future, we have to get our data. And also the thing is that it will not going to break, and also like PubSub architecture will be there, so it will going to have the even though some server is down, then also we do have the information about that data and all. So finally, we will going to from backend, we will going to store it in our traditional database. So traditional database, now you think that I said like we cannot store that much data in traditional database, then how you are telling again that how we will going to store in traditional database. So I'm telling that maybe like first time 30 days data we will store in traditional database, and like that we do have some DBGM and all, like which is the like a write ahead logic and all. So we will going to have first store in our traditional database all the training model and all the training related high volume data and all for 30 days or 15 days, and with the help of this DBGM and write ahead logic and all, it will going to have it will going to help us to write in S3 cheap S3 bucket with the help of Apache Iceberg. And finally, we will going to delete the data from the traditional database, and traditional database have the new data also, which will come in the recent 30 days and all, so that our traditional database cost will not go higher, and all the other data that is coming from very long will be stored in Apache Iceberg data lake. With the help of that concept, like DBGM concept. So like this is the write ahead logic. With the help of that, we will going to, after storing into our traditional database, we will going to have one hook which will going to store in the Apache Iceberg table. So the thing is that the cheap S3 storage. Now, finally, the thing is that when we do have lots of data and all, then we will going to train our any kind of LLM model, and with the help of RAG and the similarity score and the vector index that we all know, that with the help of that, it will going to give the output. So when we do have also petabytes level of data, so it will going to, when somebody will able to test that what kind of work it is going and all, so finally it will going to check from the cloud, from the Apache Iceberg stored, that data is there or not, and depending on that, it will going to give the similarity score, and the similarity score will going to give the output to the LLM. So that is all about the pipeline, especially we are developing from backend Express API to with the help of this DBGM and other S3 bucket and all. With the help of that, we will going to have Apache Iceberg data lake, which is very, very cheaper for especially Gen AI ready application. So, and the feature of the Apache Iceberg, like acid reliability. So the thing is that even anything will anything will change in the traditional database, or it will going to like that division hook will going to automatically change it in the data lake house. Even though there are lots of data and all, they have the feature to deal with that long kind of database, like petabyte level of database, and it will going to query in ON time, or sometimes even ON time also, and it will going to grab the thing, and it will be acid compliance with that amount of data also. It will not going to break in between and things like that. Like that, we do have a schema evolution that we can add also, change also the data which is already there in the cold lake and all. And we do have time travel feature, snapshot feature, that we want the data for that particular time being like 5 months ago, 7 months ago. I want LLM output to be in that fixed time window only. Then we do have that feature also. Especially the beauty is that we are talking about that huge amount of data. So that is the thing, and it is like Iceberg, with the help of Iceberg, we are dealing with that huge amount of data, and these are the feature of the Apache Iceberg. So this is the thing, like little slide issue. So traditional data lake have this thing, and Apache Lakehouse have this feature that I already said, that acid thing, syncing with the syncing feature, automated metadata driven, it have all the metadata of like how they are querying with the petabytes of data. Usually they have the metadata of all the data, like whatever they are feeding into, they have the metadata, and with the help of that metadata, that we as a developer also know that indexes and all in traditional database and all. So they have related to that, they have some metadata, and some expert already gave some concept about that, about the like Apache Iceberg metadata feature and storing capability and all. So this is the thing, that finally the pipeline thing, that from Express, we will have Kafka stream, so that it might happen that right now we are feeding into S3 bucket or any kind of cheap bucket with the help of Apache Iceberg. Later, we want some other service also to listen our changes, and also that's why we will going to go with the Kafka stream, and we will going to have change data capture with the help of Divisium and all. And finally, the RAG pipeline will going to work. And finally, our training will be able to complete, and our train will like our model will be there with that much petabytes of data with very, very cheap, like maybe 70%, 60% cheaper than any traditional database that we will going to deal with the RAM and all. So that's the topic about this talk. So like that's it. I think I have to wrap it faster also. So yeah, any question?
I'll take one question. Are you able to hear? Can you a bit louder, a bit louder?
Yeah.
Hello. So basically, in a traditional database, right, based on the changes, you are storing it into a analytical database. It's as simple as that. But the point is, if you are moving the data by itself, then what happens is like if you have an application, so your application data query starts breaking, right? You need to have a specific data query written, because your the data query is written for your current traditional database, right? That's how your application is built for that. So how do you manage that?
So the thing is that whatever the information right now we are feeding to our LLM from starting, we do have all the thing in the S3 bucket, like cloud storage bucket.
So you are just replicating, or you are moving the data?
No, I'm not moving the data. I'm just replicating the data. I'm replicating the data, like you can take it is a replica. So whatever our traditional database do have,
it's just a replication. You're not moving the data, because
replication of data, and finally from traditional database we are kicking it out after some time, so that our cost.
That's what I'm asking, right? If somebody makes a query to get the older data, so that data you have to have a separate query written in, because that application that you can't.
That's why this pipeline is there. Now it will not going to directly hit from your traditional database. If it is not there, it will going to hit from the S3 bucket, and with the help of Apache Iceberg, it will going to query that data in a fast manner with the help of that metadata and all, even though we do have lots of data there in petabytes level and all. Okay. Thank you.
I really felt like I boarded a very fast express, one of the fastest stop that I've ever heard. I'm very sure he was more worried than us about the food. So, all right. Thank you, Shreyansh. And then with this, we are done with the official talk lineup. Folks at the back specifically, this might be of interest for you. So we have senior TA advisor, uh, talent acquisition advisor, Vaibhav Gupta with us, representing Cloudera. If you are looking for opportunities, I think this is a small, I have put him down on a watch like for about 60, 90 seconds and he has promised not to take more than that.
Yeah, first of all, thank you everyone here for joining the today's session. And trust me, I won't take more than a minute. So as Parth mentioned, my name is Vaibhav and I'm a part of our talent team here at Cloudera. I quickly wanted to talk about, we couldn't resist to have you guys on board and losing out an opportunity to present a few of the role with us and maybe see you as few of your future colleagues. So I quickly wanted to talk about Cloudera. It's one of the best company. Trust me, I have spent 10 years in the industry and one of the best company I have worked with. We have lots of perks in future for all of our employee. Like you all can see. I won't gonna go deep. So we have global unplugged days. In fact, we are having the unplugged days starting from next week. Then we have very comprehensive work culture, employee assistance program, career progressions, right? So any one of you who are interested, who are looking out for a job or who would be looking for any future opportunities, want to refer someone whom you know, great, please free to scan the QR code of Cloudera career website and Cloudera LinkedIn page. And I am here in the session. So anyone wants to just have a quick catch up, please feel free to do so. Again, when I'm saying that Cloudera is the best company to work with, I am also talking with a proof. So we recently won rank 17 with a competing with more than 5,500 companies in India as a best place, a great place to work. And this is again not only IT. So yeah, it's one of the best company as I've mentioned. So please feel free to meet me and catch up for any discussion you want guys to have. Thank you. Thank you for your time for today.
All right. We have Rupen representing DataZip, who's a people manager, and he's again going to talk about the culture and the hiring opportunities at the DataZip.
Yes. Thanks, Parth. 2 minutes, and then afterwards I can do my 30-minute presentation. Is that okay with all of you? I've been informed that food will be 1 hour delayed also. I'm just joking, guys. Just relax. Okay. So basically...
They'll kill me.
Sorry?
They'll kill me.
They're leaving.
They'll kill me.
They'll kill you. Okay. So, hey, this is a Cloudera sponsored event, so I will just maintain the guidelines. Okay, fine, guys. Just 2 roles that we're hiring for mainly. I think my colleagues Merlin and Ankit both did a great job explaining the problems that we're working on. Fundamentally, we're looking for software development engineers to work with a smaller team. If you can just see our team, is a much smaller organization right now, which means 2 things, right? And especially, it's great that we all have gathered over here today, talking about data, talking about Apache, Iceberg, and all of this. One thing is, if you work in a smaller team, there's a lot more ownership. We're a very high ownership team, and especially given that we're open source, the stuff that you'll be working on will be directly in production. So that's something that's good. And the second thing is community, because we're all part of this community and we're trying to grow this community. And for you to be part of this open source community, contributing to something that's at the cutting edge of this industry, this is a great opportunity. So 2 specific roles. One is a Golang heavy role, and which is the first SD2 Golang platform role, which is for the managed offering that we're trying to do, which means a lot of people who are adopting our technology on open source, if they want auto scaling, if they want us to take care of stuff, they will pay for it. And that's the pod that you'll be working on. And the second role is the Java heavy role, which was for Olake Fusion, which was much discussed in today's talk by my colleagues, which if you have Java experience, it'll be really great. There's a QR code that I'm going to show you, which you can scan right now, which I'm just going to keep for some time. And if you are interested in this, any one of us who are wearing Olake t-shirts or me, you can speak with me and I'll be very happy to talk with you. Thank you so much, guys. That's it. I'm not going to keep this long.
All right, folks, on behalf of all the speakers, on behalf of Cloudera, and E6 Data and DataZip. We'd like to thank you for coming on a Saturday morning again, bearing us until late afternoon or early afternoon. I'm sure all of you are, including us, are very hungry. So just wanted to extend a token of appreciation and thank you so much again.